Recordamos, grabamos esta sesión. Got it. Okay, so that being said, what page are we going to start on today? We are going to start on what is numbered as, in the book, 46. And we're going to get through a good amount of stuff today because we did a lot of the math already. Well, for those of you who are here, now is a really good time to ask questions because you've got my mostly undivided attention.
I have a question.
Mm-hmm.
Sorry, hold on a second. Oh, my hair is kind of crazy.
At least you have it.
My husband has, well, since he's in the audio business, like many years, I don't know how many years ago it was, they use the wireless microphones, right? And there was a big problem within the industry because the FCC had sold off a bunch of white space, or I guess some of that space, and it really just kind of messed up all of these microphones, these wireless microphones that they had bought and sold, and they were in the industry, and like now they were like illegal to use them
and useless for that matter because they got interfered with.
Right. So my question with that, I mean, if FCC can do that, I mean, that kind of ruins an industry in a sense. Where does the FCC get their authorization to do that? Because I mean, that really screwed up a lot of people.
They get their authorization from lobbying, honestly. So what I can say is I personally see a value in what we do with the amateur bands as far as providing a service to everyone. See, that's ARRL. I believe even if you don't particularly like the way that the organization is run, and there are a lot of people who will complain because there are a lot of people who complain about everything.
Yeah.
If you get a ham license and you like our frequencies, you support the FCC, you support the ARRL because they're the ones who talk to the FCC and go in front of Congress and lobby, because one person doesn't have much sway. 180,000 people have a little more sway, especially when it comes to, going up against, let's say, a satellite network lobby, which has an unlimited amount of money to throw at those frequencies. That's how frequencies get bought and sold.
Okay, that's kind of what I was wondering about. Like, how does this happen?
It's about lobbying. We are what I would call an anomaly, because we're basically sitting on billions of dollars of frequencies that occasionally get impinged on, or taken away, reallocated, etc. If we don't use them, we're going to lose them. So if you see the benefit, then you should enjoy using it, and basically that use justifies its existence after 120 years.
So in terms of like using it, it's just getting on there and just communicating with the world. I mean, that's us using it.
Communicating locally, communicating with the world, showing that it's operators who are basically given the ability to use these frequencies, and essentially with the exception of a licensing fee, which isn't really it's not a use fee, it's just a processing fee, don't have to really pay anything to do it. We have to, if we can say, hey, you know what, we don't pay anything for it, but the intangibles we provide, which is that, when something goes wrong, or when there's, new technologies that the whole world can end up using, we're the ones on the forefront of developing them as a hobby.
How about the equipment? Like, what becomes of this type of equipment? Because I asked him, I'm like, well, what do you do with it? He's like, nothing. It just sits there on the shelf. It's all like proprietary, like equipment that has been, made by the companies. And it's not like we're, you can't, without the knowledge, I guess, to change things around. I mean, you have obsolete stuff. So, Does
Well,
it become
like
obsolete, or can you just actually, because what you taught yesterday was a lot of stuff, and I felt like
it's
anything that you have, you can kind of mess with, and then
it's that's right. That's right.
and
That's
make
right.
frequencies that work.
It's the stuff behind the stuff.
Right.
We're ham radio is different because we're not appliance users. For instance, like you've probably seen at some point a radio that looks like that.
Yeah. Mhm.
Okay, family radio service.
Mhm.
$40 a pair, and they have a certain number of frequencies available to them. It's typically 14 to 22 channels, 38 different subtones, which we're going to get to. But you notice those antennas, you're not allowed to take them off. You're not allowed to hook it up to anything else. You can operate on channel 1 or channel 2 or channel 3 or channel 4, et cetera, et cetera, et cetera. It's a channel, so it's a channelized service. The frequencies are very well defined. FRS channel frequencies. Here they are. Those are the channel frequencies. Those cannot be changed. You want to go halfway in between two of them, you're not allowed to do that. Right? The service does not account for that. There's essentially nothing written into the service that says you're allowed to do that. You're also power limited by the license. So, okay, so you're limited in frequency, you're limited in scope, and you're limited in antennas. The ham radio rules, Part 97, are intentionally vague because instead of like getting a GMRS license, like so GMRS is basically like the next version up from family radio services, general mobile radio service. You pay your $35 and you can get your family a license to operate, right? In theory, you can remove the antennas, but you're still limited to power and channels and stuff like that. Now we look at what we have in this band plan. Did that pop up or not? It did not. Okay. So this band plan right here, now it should pop up. Okay. So let's look at, let's say, the 2-meter band. All right. Notice that there are no channels specified, and I'm going to zoom in on that. There are no channels specified. It just says from 141.4 to 144.1, there's Morse code, which is CW. 0.1 to 0.3 is no FM, single sideband. And then above that is satellite. And then this orange stuff is repeaters and simplex and some other and more satellite stuff. Does it say thou shalt operate on a frequency of 144.125? I don't see that anywhere. Not in the rules. So basically, what we have, by virtue of the fact that we've gone through training and we're basically assumed to know more than just an appliance user, is that when we go to, let's say, this radio, and we're going to pull this up on the screen. This is a little more expensive than most people have, but let's pull up the ICOM 9700. Come on. Okay, so these are both amateur frequencies. This is a tri-band radio, costs about $1,700. It's basically set up for satellite operation and lots of other stuff. Now, that top frequency you see there is set for 433.0, right? The bottom one set for 1295.1. The only thing that's stipulated in the rules is that you must be between 420 and 450, or between 1240 and 1300. You can tune literally anywhere. There's no saying that you must be on a certain channelized frequency. Again, that's one of the things that we're allowed to do. And unlike a lot of other services, you can build your own antenna, you can hook up your own antenna, you can build your own station, you can adjust your power level where you can't in a lot of other services. So use it or lose it, as they say. That's why we're all here. And I suspect we'll hopefully have a flood of people coming very soon because maybe a late arriving crowd. We're a little bit small right now. All right, before everybody else shows up, any other questions before
Are you a fan of the Anytone radios?
it depends. I think of the Chinese radios, they're not bad. How's that?
Because my brother wants me to start doing the whole DMR thing with him.
They're not bad. I actually have one.
Okay.
I mean, I think they're a lot easier to program than a Baofeng, and I think the front end filtering is better than a Baofeng. So
Sure.
of the Chinese radios and the fact that they do DMR, they're not bad, I would say.
Okay. And there's also a company that provides you all set up and everything done already with a hotspot. I forget the name of that company, but that's what he suggested me go through.
Is it Zumspot?
I think so.
Yeah. I don't have one, but I've heard of them. And typically if they're one of the places to look is on eHam and look
Right.
at product reviews and see what people think.
Thanks,
And
Scott.
those are see now here comes a little bit more of a flood of people. All right. Any other thoughts or questions before we get started today?
Hey, I just wanted to let you know maybe one of the reasons that you're seeing fewer and fewer people. I know in Mike and probably my daughter and her husband, we signed up separately, and my wife and I started logging in on 2 different computers.
Oh, okay.
We weren't sure if we needed to be logged in all the time to get credit or whatever, but now we're just one of us signing in and watching together. So that might be part of why you're seeing fewer people there.
Yeah. So it's actually the same number of people, but fewer logins. I'm okay with that. Doesn't bother me. I mean, I've taught as few as 5 people before. So.
Hey, Scott.
Yeah.
Just so that you know, Jim Kilpatrick and I have been logging in every day together also.
Okay.
So he's been on. It's just he's been watching through my connection.
Cool. Okay. Yeah. I mean, I don't mind. Like I said, by the end of class, I've started with as many as 50 something, and I've ended with as few as like 10. So, I feel like this is one of those weird things where I don't really mind if the class gets big. I hope all the kids are still here and not, totally overwhelmed by this stuff. I see that Julie is here and Gavin's here. That's a good sign.
It is hard.
It is hard. It's supposed to be a little hard, but you know what? Out of difficulty, you know what you get out of that?
Accomplishment.
Accomplishment. Yes, very good.
License.
And licensing, and something that other people haven't done, which can tend to, it gives you skills. It gives you skills you can apply. So, this is a really interesting avocation, I would say. Not a vocation, but an avocation, because it's, you basically not paying for it. You're paying for it with effort and time. And in today's world, I mean, we're not really used to playing the long game on a lot of things. Everything is so immediate.
Isn't this class typically taught over the course of a month too, like once a week sessions? Isn't that
Depends how you teach it. I've taught 2 classes that were once a week, twice a week. But, I mean, I find it difficult unless I'm teaching Morse code. You can't teach Morse code in a day, right? So I have to spread that out.
What's a good resource for learning Morse?
I teach it.
Okay.
There's also something called LCWO, which is an online program called Learn CW Online, and it uses something called the Koch method, which is a way of learning slowly but with high character speeds, which is typically what I do as well. That gets you used to hearing the characters fast and
Gotcha.
allows your brain time to kind of recover in between letters. There's also, for instance, CW Academy.
Okay.
And there's another one called the Long Island CW Club that runs classes. And those are all online. I actually do online classes. The trick to doing online classes is that there's this little button on Zoom that says original sound for musicians, and you turn that on because otherwise Morse code is considered noise, and it just kills it. So,
Right on.
all right.
Well, back in 1991, I fished with a guy whose best friend was the national champion, and he was, what, 18 years old or so. I don't know how many words he
Morse code?
typed. Yeah.
It's probably somewhere in 70, 75 words a minute. I've never gone that fast. Okay, so I just put out in the chat the link to the book that has the page numbers. So I went out to the website and I actually downloaded the book again, and this one has page numbers. So in between the time that I last did it and this time, he updated the free book, which I believe now has page numbers. So now I can look along with page numbers with everybody else. So let me see where that is. Okay, well, it looks like everybody's about here. Do we have any more questions before we get started? Today's going to be a busy day. But like I said, most of the math is gone. We're done with most of the math. And we are starting with antennas, which are still, after all these years, my favorite thing. Because they are what allows you to make the biggest difference on the air, more so than any radio or any kind of modulation technique or anything. And you can build them, and they cost almost nothing to do if you do it right. You can spend lots of money on an antenna, but you don't have to. Okay, so we are on what is now listed as page 46, because I now have the numbered book. So it says antennas and feed lines. So we're just going to start with antennas and feed lines. And what we're going to do is draw, once again, the surface of the Earth. And I guess it's the ocean today. So we're going to draw two antennas. The direction of the antenna defines the polarization of the antenna. So this vertical one will be vertically polarized. This one will be horizontally polarized. The reason is that the electrons move back and forth. The electric field is the direction of the wire, typically. So a vertical antenna will have a vertical polarization. The E field will be going up and down. And a horizontally polarized antenna will have an E field or electric field that is going side to side, parallel to the Earth. Practically speaking, again, there may be a little bit of improvement for a horizontally polarized antenna over a vertically polarized antenna when the electric field strikes the Earth's surface. But to be honest, depending on what you're doing, that really determines which one you're going to use. If you're trying to talk locally through repeaters, you'll typically use a vertical antenna. And that's usually for VHF and UHF, or if you're trying to go for a low angle of radiation, which we'll get to in a minute, vertical antennas are great for that. A horizontal antenna is typically going to radiate broadside to the antenna. All antennas transmit perpendicular to the axis of the antenna. So notice that there's some energy going straight into the ground and some going straight up into the sky. Whereas a vertical antenna will be going everything parallel to the Earth's surface. So in some ways, a vertical is a better antenna for long distance communication, depending on how it's built. A horizontal antenna can very often be a lot easier to put up, and because it's directional this way, when you rotate it, if it's rotatable, you can have it steerable, whereas a vertical antenna, you cannot, the way that it's built. Okay, so what we're going to do is draw our very first antenna. We're going to draw a piece of wire that is 1/2 wavelength long. Whatever that frequency and wavelength are, it's a half wavelength long. So here's the first question. After we discussed yesterday, a node is a spot on a piece of wire. What is the current at the end of the antenna? Remember, what is current?
Low.
No, what is current? Current is,
Voltage.
The way
nope,
something.
not voltage. Current is movement of what?
Electrons.
Electrons.
Okay, so at the end of the antenna, what is the current?
The same as it went in.
No, has to be zero.
Zero.
Oh,
Electrons have nowhere to go. They're physical. What is it at the other end? Also zero. And what does a half wave look like? Well, if I draw a full
That
wave,
would be maximum current. Maximum current.
well, a full wave looks like that, right? That's one full wave. Well, I said that this antenna is a half a wave long, so obviously I didn't draw
No.
that wave very well. A half wave will look like this. And that is the current distribution. And what do you notice about the endpoints? The current obviously has to be zero. So I drew this correctly. Yay. Okay, so now if I have this antenna, which has maximum current in the center, and I decide to take this antenna and break it right in the middle, and I feed this antenna with some kind of feed line, which is either coaxial cable or twin lead, which is your ladder line or your old school television cable. What I end up doing is I have to have a measurement of what my impedance is right here. And by Ohm's law, what is impedance? E is equal to what?
I times P.
Nope. Got to
I times
remember.
R.
Got to memorize this one.
I
E
times R.
equals I times R, except that in this case it's impedance and not resistance. So we're actually going to use Z for impedance. Okay. Now, what do I know? E, I, Z, like that. Okay. We don't know our impedance. We don't really know our voltage and current either, but we kind of have an idea. So what we're going to do is something called a WAG or a SWAG, which is a guess. Z is equal to E divided by I. And what is our I? This is our current at that point. Is it high or low? If you had to
Low.
guess.
Low.
No, actually the current is high. Remember, that green line is the current. The current at the end would be low. Comparatively speaking, what's the current in the middle?
Highest.
Maximum.
It would be
Max.
high, yeah. Okay, and we'll call that high. And it turns out that where your current is maximum, your voltage is probably pretty low. This is kind of an assumption that is usually true. So we're going to say that it's low divided by high. What is low divided by high?
It will go into negative value or
No,
zero.
it's not. No, it's not negative. What's something that's low divided by
Middle?
something that's high? No, it's not zero.
1 divided by 1,000.
We'll just call it low.
No.
So our impedance for that antenna is what we would just call low. Now, we're going to take this antenna and instead we're going to erase this right here. Going to get rid of that feed line. And instead, we're going to put feed line all the way at the end. And we're going to break it way at the end. Okay? What is our current right there?
Very low.
We're going to do E equals I times Z again. E, I, Z. And now we don't know our Z. Z is equal to E divided by I is equal to something divided by low.
High divided by low.
And that would be high voltage divided by low. And which is high.
High.
So our impedance at the end of the antenna would be high. Our impedance at the middle of this antenna would be low. So does it matter where you break it? Because if you think about it, can we change the way that this current looks? at a given frequency and wavelength and an antenna length, can we change it?
No.
No,
Yes.
because it's governed by what?
Flow of electrons.
That is governed by physics. We cannot change it. The only thing we can change is how we get power into it and what the impedance is where we feed it. This antenna is known as a half-wave dipole, and its radiation pattern is broadside to the antenna. So we have antenna radiation going up and down and toward us and away from us. How much energy do you think goes this way along the wire? How much radiation actually goes that way along the wire? And the answer is basically nothing. So this is a really kind of special antenna because the radiation pattern basically makes a donut shape around the antenna. So some of the energy goes up, and some of it goes toward us, and some of it goes away from us, and some of it goes straight down. The straight down, again, doesn't really do us a whole lot of good. Straight up doesn't do us a whole lot of good. But the stuff that's going forward and backward, yeah, that's really helpful because we can take this whole antenna and rotate it and change where those where that beam pattern is. All right, so this is a half-wave dipole. It's the fundamental antenna that exists basically due to physics. Well, now what we can do with this antenna is we're going to add something to this antenna because we don't really like that energy that, let's say we want to send energy in one direction. So we're going to make a half-wave dipole. All right? And typically we're going to feed this in the center. We're going to break it and feed it in the center. How long is this antenna? And the answer is right up top.
Quarter
Yeah.
wavelength.
Quarter wave on each end.
Yeah.
For a total length of?
Half wavelength.
Okay. So what does that mean for how, if I pick an antenna length that's 33 feet, how many frequencies is that a correct antenna for? Once I assign a length to it, how many frequencies is that a proper length antenna for?
One.
One. That's right. It's a perfect antenna for one frequency, which is why antennas can get a little tricky, especially if you want it to operate on multiple bands. So let's just say that this antenna actually is, we're going to say that it's 33 feet in length, which is a half wavelength. Okay, so can we figure out, this is actually roughly 10 meters. Can we figure out what frequency this is supposed to work on? Do you guys remember that formula yesterday?
300.
That one? Okay, so we don't know our frequency. Equals 300 divided by lambda is 300 divided by 10 meters, which is about 30 megahertz. And in fact, that is approximately, because of slight, being slightly off, which we're going to get to, this is roughly a 28 megahertz antenna. Now, if we go back to our frequency spectrum chart that's available to us, we find that, what band is that cut for?
10 meter.
That would be 10 meters, except I think I made a mistake. And the reason I made a mistake was because I did make a
33 or
mistake. That's right. 33 feet is a half wavelength. That's right. 33 feet is a half wavelength. So a full wavelength is actually 66 feet, which is 20 meters. So we're going to do that again. 300. It's just more opportunity to practice, right? 300 equals 300 divided by 20 is 15 megahertz. There we go. That's more like it. So now we're going to look back at our chart. and see that it's basically, there we go.
Wouldn't it be easier to do your antenna length in meters as well?
Yeah, it would.
Okay.
But being that, the United States is basically feet and inches, we usually cut things in feet and inches. But it's important to know how to convert from, feet and inches to meters. Roughly 3.3 feet per meter, or about 39 inches.
So how does this relate to the I think at the beginning of like on Monday you said that antenna need to be like a quarter wavelength in order to like properly receive. Like how does that relate to what we're talking about here?
We're getting there right now.
Oh,
because we just built, let's say, a half-wave antenna that's 33 feet long. That is cut for the 20-meter band, so that is a 20-meter dipole. Okay, so if we were to draw the 20 meter and 20 meter signal, we would find that we would get a full half wavelength on that. That is a resonant antenna.
Isn't 20 meters 66 feet?
Yep. Except that this is a half wavelength antenna. So it's a half wavelength long, which makes it.
Can you explain what that means again?
What?
Can you explain what a half wavelength is in this case?
Yeah, well, a full wavelength is 20 meters. So a half wavelength is 10 meters.
For this one, you wrote 33 feet,
Yep.
10 meters. I mean, you wrote 20 meters.
Right, because it's cut for the 20-meter band. That's the range of frequencies we're attempting to get. So it's set up for the 20-meter band. So this is a 20-meter receiving antenna. But we know that a half wavelength is 10 meters long.
So the band you want is the length of the antenna, total length of antenna?
No.
No,
A full wave antenna doesn't work. It works, but it's hard to feed. A half wave antenna is an easy antenna to build. So whatever band you want, you
No,
take
I
a
mean,
half wave.
the line you have drawn shows 66 feet, correct? You have done half.
If I were to take this antenna and build it, it's 33 feet total. This would be 16 feet, and this would be 16 feet. Roughly. 16.5.
I'm a bit confused here.
Can you do an example backwards and choose
Sure.
a frequency
We will
and
do
then
that.
determine the antenna
Yes.
length? Maybe
So-
that will help.
So we're going to do an antenna for 50 megahertz. This is in the 6-meter band. Okay, so we're going to make an antenna that works on the 6-meter band, and we're going to make a half-wave dipole. Okay, so the first thing we're going to do is we're going to use our formula 300 F and lambda. What's the thing we don't know? We know we specifically want it for 50 megahertz. So even though it's the 6-meter band, we're not going to use that directly. So we're going to use our frequency, which means we don't know our wavelength. So our wavelength is equal to 300 divided by 50 is actually equal to 6 meters exactly. Okay, now we said we want a half-wave antenna. How long is a half-wave antenna?
3 meter.
3 meters. Okay. Now, there's a fudge factor that we have to do. We have to shorten any calculated antenna length by about 5%. And that's because wire is not perfect. It has self-inductance, and it couples to things in the world around it, like air and like, buildings and stuff. So in order to make an antenna resonant, there's also something called a velocity factor, which tends to shorten up the antenna slightly. So we knock off 5%, which means we're left with 95%.
What did you call the factor?
That's called a velocity factor. The velocity factor is basically how fast how fast an electromagnetic wave travels along or inside a certain medium. So there's that magic 95%. So, okay, so 95% of 3 meters is 2.85 meters. And now we have a conversion factor, 39.34 inches per meter. And I got to grab my calculator unless somebody can beat me to it. 39.34 times 2.85, we get 112 inches. So if you're building a 6-meter half-wave dipole for exactly 50 megahertz, it will be 112 inches long.
And that does.
Go ahead.
One quick question, and that doesn't matter whether your coax is at one end or in the middle?
This is a resonant antenna. It has no, the position of the feed point has no bearing on it whatsoever. This is the proper length of a resonant antenna that's a half wave long. If I were to draw this antenna and I were to have it operate at 50 megahertz, I would have 0 current on this end and 0 current on this end, and I would get a full half wavelength appearing on the antenna. And it would be a total 112 inches. And if I fed it in the middle, it would be 56 and 56. Now, I could also feed it, if I wanted to, right here. And I could make it so that it was 38. And let's see, that would be 74. I could do that. Now, the only disadvantage to doing that is that if, depending on how I feed it, whether I feed it with balanced line, like ladder line, which looks like this, just 2 parallel wires spaced with it's also known as window line. It kind of looks like that. And you have the 2 wires running inside it. Or if I have coaxial cable, which looks like this. This is what we think of when we think of like cable TV cable. This is an unbalanced line because you have the inside conductor and the outside conductor. So those are not balanced current-wise. Well, it turns out that if I feed this antenna right in the middle, I get something close to a balanced antenna where I have balanced currents, which will force me to have a nice equal currents on both sides. If I feed it off to one side, or this happens to be like, closer to a house, then it might be unbalanced. The purist might say, okay, well, we need something called a transformer that will force the current on both sides to look exactly the same. And that's known as a Ballon transformer, or a balanced to unbalanced. It can also be an unbalanced to unbalanced transformer, which is called an un-un. But for the purpose of this class, we don't really need to know that stuff. Just keep in mind that they exist, and they can be used to make an antenna pattern look prettier. So now,
Alan,
go ahead.
Did you say balanced transformer?
Balanced, well, there's a Ballon, which is balanced to unbalanced. And then there's an un-un, which is unbalanced to unbalanced. So basically, an unbalanced to unbalanced would be like coax feeding coax, because coax is unbalanced. And a Ballon is coax feeding ladder line. Ladder line is a symmetric cable, so it's balanced. Okay, so now we're going to just briefly go over the concept of an antenna pattern. So if we draw our current that goes like this on this antenna, we feed it in the middle. We really don't have to feed it anywhere. We just have to know that the current exists on this antenna in that pattern. So if we were to take this antenna and break it up into a whole bunch of different little pieces. Okay, everyone agree that antenna is now sliced into a bunch of little pieces? One could now say that on this little segment of antenna, we have an average of this much current. On this little segment of antenna, we have an average of that much current. On this little segment of antenna, we have that much current. So we could do this for the entire antenna, and because current is what generates electromagnetic fields, we can now take a look and say, okay, well, if we really want to, we'll pick this random point in space, and we'll take this little segment and figure out what the energy, the radiated field looks like from that spot. And then from this spot, we'll do the same. And then from this spot, we'll do the same. And from this spot, we'll do the same. Now, if you then take this spot and move it from here to here, and then here and here and here and here and here, and move it around, what you will end up with is something that is called a radiation pattern, which is a representation of what the antenna is actually doing, what the signal looks like coming out of the antenna. So for this particular antenna, if I were to draw this antenna, we would find that the radiation pattern looks like a donut that looks like that. Actually, it goes all the way like that. And that this surface goes around, and this is as best as I can draw it. Essentially, it goes up and down and back and forth. So really, this should be drawn like that. There we go. And it's in the shape of a donut. So the strongest radiation is perpendicular to the wire in any direction. So that could be up or down, or it could be straight down or straight up. And this is known as broadside to the antenna. So a dipole antenna will have a radiation pattern that is broadside to the antenna. Now, the other thing we can do with this, though, because we don't really care about that stuff that's going straight up, and let's say that if we draw this from above, we get energy that goes that way and energy that goes that way. What if we want to try to talk to somebody over here, and we really don't care about the people behind us? Well, isn't that energy that's going out to the back kind of wasted? I mean, if we don't want to talk to them, and then what ends up happening is we actually hear stuff equally well because the antennas are, they have what's known as reciprocity. Their pattern on transmit is the exact same pattern that they receive better with, which means if we hear stuff from behind, that means we'll also be transmitting to behind us. Well, what we can do is about a quarter wavelength behind the antenna, we can put a slightly longer piece of wire. And this is, somebody already guessed it, known as a reflector. And what this does is it essentially gets in the way of the energy that's going this way and re-radiates it in the forward direction, essentially creating sort of like a brick wall, so that energy going backwards is re-radiated going forward. If we still have too much signal going backward and we want more going forward, we can actually put another one here called a director, which is a smaller antenna, or a smaller piece of wire, about a quarter wavelength away. And then, after that, we can put another one about a quarter wavelength away, and we add more directors. This is known as the driven element because it's the one that's receiving the power. The other elements are known as parasitics. And what they do is they're basically like parasites. You know, they sort of like feed off of the host energy and make it do something special. What this does is it takes the energy that was going backwards and redirects it in the forward direction. And it takes the energy that was going in the forward direction that was going this way and kind of redirects it so that it's straighter. It makes an easier path so that your overall antenna radiation pattern looks like that.
So is that why when you look at antennas, you'll see like a bunch of pieces of wire kind of all lined up? Is that, is only one of them the actual thing that's producing energy?
In most cases, yes. There's also something called a log periodic where they're all driven, but for the most part, a Yagi antenna. This is known as a Yagi. And, oops. And technically it's a Yagi UDA. UDA gets kind of short shrift. But those were the inventors of this antenna. And this is a directional antenna. And if I were to draw what the radiation pattern would be in strength, it would look like that without being changed. That would be the 0 line.
Now, the buddy hex that you guys showed us, is that a directional antenna also?
It is. That's actually a differently shaped Yagi.
Okay, thanks.
So we also now have this radiation pattern that extends considerably further forward. And if this is our line of 0 decibels, that's our reference point, how do you think we would measure the gain? What units would we use to measure the gain?
Decibels.
Decibels. So that this would be something like, 8 dB. And if we were to draw this and say, here's the 4 decibel line, and here's where the intersection is, this would be known as the antenna's beam width. Because, actually, sorry, that should be 5 dB. Why can't I erase? There we go. That would be the 5 dB point, because it's 3 dB less than the peak. If the peak is at 8, then the 3 decibels less point would be 5, and then, so this is known as our 3 dB beam width. And that's how we measure the beam width of an antenna. So if I were to take this antenna and add more stuff to it, let's say I had enough room or a high enough frequency that my wavelength was sufficiently small where my antenna looked like this, what do you think my radiation pattern might look like from an antenna with that many things? Just take a guess.
It'd be more focused, like
Be much more focused. Yeah, the antenna beam width would be narrow, and there'd be very little energy sneaking off the back. So this antenna might have a gain compared to a dipole of 20 dB. And what is 20 decibels? 20 dB is 10 dB plus 10 dB. Every time I use 10 dB, how much multiplication do I get?
10.
10 times. Which is?
3.
100.
10 times 10 is 100. Which basically means if I have a 1 watt transmitter, this antenna gives me the equivalent of 100 watts of forward power in that one direction. And that's why we use directional antennas. That's why if you are attempting to, for instance, let me show you guys a quick picture. Here we go. EME array. Okay, can everybody see that?
Yep.
Everyone, okay. That is an array of 16 individual 1.2 gigahertz Yagis, each of which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 elements. So each of those antennas compared to a dipole is maybe 10 or 12 decibels of gain, and there are 16 of them in a 4x4 array. And what is the purpose of building something like that? Anyone know what EME is? See, this is called EME arrays.
Electromagnetic emission.
EME stands for Earth, Moon, Earth. So basically, this is an array that is used for what is known as moon bounce. So you would take like 1,000 watts and you'd add 30 decibels of gain to it through lots of antennas and shoot it at the moon. And somebody else on the Earth would be doing the same thing, and you would basically bounce signals off of the moon. And that's why we do things like that. that can also be used for terrestrial purposes. I mean,
Does-
a microwave link, because microwave links are going to be very high speed and very focused. They're very, very short wavelengths. And what's the point of, spreading out a microwave signal in all directions when there's nobody to receive it?
Does direction matter?
Direction in what way?
When you say you want to shoot it off the moon, let's say the moon's behind you and you're shooting it forward.
Oh yeah, you won't hear the. I mean, you got to aim at it. I mean, your beam width is going to be like a degree wide or 2 degrees wide.
The antennas are fixed, so do they not work some of the time?
No, they're all rotating. They're all on. It's a gigantic as-L rotor that moves the whole array, kind of like a telescope.
Got it.
So when somebody's on the, say the moon to my aspect is below the horizon, am I going to count on that beam to duct around the
No.
Earth?
Nope.
If I don't see the moon,
it's
I
not gonna
don't
work.
get it.
That's right. So your maximum coverage comes when you're either at moonset or moonrise, and the other person is at the opposite. So if it's moonrise for you, it's moonset for somebody else, and if you both aim those antennas right down along the horizon, and you don't have any trees to worry about or anything, you can actually talk almost halfway around the world, bouncing signals off the moon. And yes, you can do this with a technician license, because as a technician licensee, you are allowed all frequencies above 30 megahertz. That includes the 23 centimeter band, which is the most popular for moon bounce, and you're allowed an output power of 1500 watts up there. And that's not 1500 watts coming out of the antenna, that's 1500 watts going into the antenna. Good time for a little calculation. So let's say you have an output power of 1500 watts and you have 30 decibels of antenna gain.
So
All right, so what's 30 decibels?
1,000 times the.
That's 10 times 10 times 10 is 1,000 times. So your forward radiated power is
Like 1.5 million.
1.5 megawatts. In other words, don't point it at somebody. That's why we bother. That's why you bother to take a license class. That's why you take an exam. All right, somebody was going to ask a question. Nobody? Okay.
I mean,
All right.
well,
Yep.
what would happen if you pointed it at somebody with that
It would
amount of power?
cause some degree of heating to their body tissue. Not quite a microwave, but certainly not good. All right, so now we're going to look at another type of antenna, which is a vertical. A vertical is typically, in its simplest form, a quarter wave over something called a ground plane. This is an electrically reflective surface. This can be the roof of a car. This can be seawater. This can be a pie plate. This can be a cake sheet. I've used all of those. So where is we already said, what's that other antenna, the really popular one? It's a half wave dipole. That's the simplest antenna that exists, right? Well, okay, so this one's only a quarter wave long. Well, we already know that the basic antenna is a half wave long. So where's the rest of this antenna?
Is it that ground plane? Or,
Yep.
Oh.
There's the other quarter wave. It doesn't actually exist, but the way that we can sort of reason its existence is I'm going to grab a reflective surface, if I can find one in my wife's craft room, and I'm going to turn off the light if I can reach it. Okay, and I'm going to turn on my flashlight and unshare this. And can everybody see my flashlight shining?
Yes.
Okay, now ready? I'm going to move this so that this reflective surface is shining. So the light is shining on this reflective surface and hopefully is being picked up by the camera. Okay, there we go. How many lights are there? If you didn't know there was a reflective surface, how many lights would you see?
2.
Okay, are there really 2?
No.
No, but you might as well think that there are. If you didn't know there was a reflector there, you would think that there are actually two things. So what a ground plane does is it basically causes a mirror image of our quarter wave up above in like a fake quarter wave. So if we were to take then our current, we would find that it goes like this, and then there's a mirror image that to the outside world then looks like the rest of it. And if you're standing out here and looking at this antenna, what would you see? What do you see? You see a top part and
The reflected.
the bottom part. And you don't know that it's not a dipole. So it might as well be a dipole. Electrically speaking, the only fundamental difference is that this part of the antenna doesn't really exist. And if this material down at the bottom is not electrically conductive, then it does not work. So this ground plane down here really has to be a conductive ground plane in order to work properly. Now, what it turns out is that a dipole fed at the center has an impedance of roughly 72 ohms. A vertical fed right here, where the other part is tied to the ground plane, this actually has an impedance of about 36 ohms. So it's actually half of it. Well, conveniently, we're going to get to this. Most radios look for an impedance in the antenna and cable of 50 ohms. So 72, that's pretty close. 36, also pretty close. We can actually work with either of those. Those are actually pretty good antennas for us to use. Just happens to be a nice, happy accident. So, okay, so now we have a quarter wave vertical. The advantage of a vertical, let's say that this is instead the rest of the antenna. What does the radiation pattern look like from an antenna that's straight up and down? Goes that way, and toward us and away from us. How about up toward the sky? Nothing up toward the sky. How about straight into the ground?
Also nothing.
Also nothing. Well, that's actually a pretty good antenna, isn't it? Especially if you want signals that hug the Earth's surface. Can you think of any time when you wouldn't want to talk to stuff up in the sky? Let's say that this is on the 2-meter FM band, and there's a repeater over here on a building with a vertical antenna. That's only, that's 20 miles away. And it's at an altitude of 400 feet. As far as you're concerned, that's basically on the ground, right? That's along the surface of the ground. This antenna, with its nice low angle of radiation, is going to work really well to talk to that. That is actually the same antenna that's on a handheld radio. That's the same antenna that we build for the roof of a car. And so now what we're going to do is look at the roof of the car. Most roofs of cars these days are still made of metal. Because of that, you can actually drill a hole in it and then tie that to your ground plane. Or the other tricky thing is that, let's say that you have something called a mag mount. Anyone ever heard of a mag mount antenna?
Yep, use one.
Okay, it's a big magnet in a base that holds this antenna down to the surface of the car. So here's the antenna coming out, and here's the cable going in, and here's the other one. All right, so there's the cable. Okay, you see that how that green line down at the bottom there? Is that actually touching the bottom? Is that actually touching the roof of the car?
No.
Nope, it's not. But what does it look like? What is this? Everybody remember that from yesterday? What is that thing? That is a capacitor. And radio frequency is a very high frequency form of AC. Does everybody remember what happens to a capacitor when it gets to AC?
Fluctuating.
What does it look like?
The short circuit.
It's a short circuit. Yeah. Guess what? As far as this is concerned, all of the energy that goes into the bottom half of the antenna just passes right on through that space in between the plate and the roof of your car. And the roof of your car now becomes the second half of the antenna. Similarly, this is where it gets a little more interesting even. Let's say that here's your hand, a very crudely drawn hand. I can make it a Simpsons hand by taking a finger away. And I'm gonna put a radio in the hand. And here's the antenna. This antenna is a quarter wave long. Okay, what's missing?
Ground
The-
plane.
Yeah, where's the ground plane?
Is it your
Body.
hand?
Yeah.
Body.
Yep. You are the ground plane. You are capacitively coupled to the body of the radio. So what happens if you try to take the radio and just put it on the countertop? How well will that antenna work?
Won't work. as
It
well.
won't work very well. No, it needs the second half of the antenna. You, when you're holding it, are the second half of the antenna. And you actually have radio frequency energy going back and forth through you. Pretty neat, right?
So
Okay.
Does it have to be your bare hand in order to do it, or
Yeah, that's a good question. I mean, I suppose it would work with gloves, but
Mhm.
again, the more stuff there is in between, the greater the gap,
Yeah.
the worse the coupling.
or like if you had a like one of the receivers, I guess like I don't even know what you call them, the things that are not attached to the radio itself, but are kind of like you pull it up and it has like it's on a cord and stuff.
Okay. Well, I have seen some radios that look like this, where here's the antenna, and there's an accessory that people sell called a tiger tail, which connects to the ground of the case of the radio. This is a quarter wave long. It's just basically a piece of wire that attaches to the shell of the radio. Okay, Antonio Dvorak.
Sorry, that was a joke from my friends. But let's say hypothetically you had telekinesis.
Okay.
Um,
It would be a
And let's
big
say-
hypothetical.
and let's say you had a ham radio and you tried to control that with your mind. Where would the ground plane be?
It would not exist. It still has to be physical. Now, I suppose if you could astral project, that's another story. Right? I love some of these questions. Thank you for that. All right, let's see. Okay, how do you make an antenna operate at a higher frequency? What would you do with it? And by the way, we're on page 47. How would you make an antenna's frequency higher?
By shortening the antenna.
That's right. You shorten the antenna. How do you make it a lower frequency?
Making the
lengthen
antenna
it.
longer.
Making it longer. So let me ask a question. If you're building an antenna for the first time and it's 65 feet long, do you want to make it a little too long or a little too short?
A little
Too
too
short,
long.
reckon it's-
Little too long. Always make it too long because you can always trim it. It's a lot harder to solder stuff onto the end of it. Okay, so we're going to do another calculation, a quarter wave antenna at 146 megahertz. Okay, so we're going to use our formula, 300 F and lambda. We don't know our exact wavelength. Lambda is equal to 300 divided by 146 is about 2.05 meters. We want it to be a quarter wavelength long. And a quarter wavelength is about 0.512 meters, something like that. And we're going to shorten it by what percent?
5%.
5%. So we need 95% of that, which is about 0.47 meters, which translates to about 19 inches long. That is the length of a quarter wave antenna for 146 megahertz. And if you look at 146 megahertz, you will find that this frequency is right smack in the middle of what we call the 2 meter band, which is kind of like a main superhighway for ham radio communications. This is what we use on cars. This is what we use from, on with walkie-talkies. Okay, so now we can also say what we're going to do with this antenna. Well, let's say I'm carrying this radio around. Can everybody see this radio that I'm holding? This had to have a 19-inch long antenna on the end of it. Is that antenna that I'm holding 19 inches long?
No.
Clearly not. However, this is still a quarter wave. The reason it's a quarter wave long is that internally it looks like this. I have 19 inches of wire, but the bottom, I don't know, the bottom 14 inches are coiled up in a little coil. So the total electrical length is still 19 inches long, but the overall physical length is only 7 inches long. So what do you think happens to the efficiency of this antenna if I take all my current, which is, the current which is supposed to be transmitting signal, and this section cancels this one, which cancels that and cancels that and cancels that and cancels that? What will happen to my antenna?
It'll get less efficient because
It
of
gets less
interference.
efficient. That's right. You basically kill the efficiency. And
What do you
now
mean it cancels? What do you mean by it cancels out?
Well, if I have current that's going this way exclusively, it's going to basically make magnetic fields. It's going to radiate outward and such. But now let's say that part of it, I have current that goes that way, followed by current that goes that way, followed by current that goes that way, followed by current that goes that way. What's going to happen to the fields that are generated by those currents? They cancel. They're opposite. So they cancel each other, which basically means that the bottom part of the antenna really does nothing useful other than make the whole thing short.
So then why have that much coiled around anyway? If it cancels out, why have that much coiled around anyway?
Well, you need it. Because how long does that antenna have to be because of physics if you're making it a quarter wave? It has to be 19 inches long. Now, it would be better if you could make it like that, if you put the coil at the end, because then your maximum current would be at the bottom. That would be a more efficient antenna, but then your antenna would basically be really, really skinny and have a big ball at the end, which would make it droop over. That's why we don't do that. It's basically physics meets, construction. So now let's take that antenna and say that our gain of this antenna compared to what we have straight up and down, which is really long, has a gain of negative 5 dB. Is that good or bad? What do you think?
It's bad.
It's pretty bad. Yeah, it's actually pretty bad. It loses like 75% of the signal. That's actually pretty darn bad. But what if the repeater that you're trying to talk through is a mile away? Distance of 1 mile away, and your receiver has it can receive anything at a negative 120 dB compared to a milliwatt. And this thing, by the time this gets here, this signal is 1 watt, and the signal that's received at the antenna is minus 110 dB M, and your receiver can receive anything down to minus 120. Well, okay, so minus 110, this is where we start to get into systems and adding things together. This is the strength of the signal that gets to the antenna, and you knock off another 5. So what is minus 110 minus 5?
Minus 115.
Minus 115, which is still bigger than minus 120. So even with the crappy antenna, your system still works. But now what if you're further away, and instead of being 1 mile away, you're 20 miles away? And your signal that's coming in is minus 118 dBm. What's negative 118 minus 5?
123.
Minus 123. And you will no longer be able to receive that signal. However, if you switch to the other antenna that doesn't have the loss, it's minus 118 minus 0, which is minus 118. And you will be able to see it, to receive it. So using an antenna like this is exactly the reason why some people, in addition to having their portable antenna, which is on their radio and very easy to carry around, will also bring along an antenna that they can stick on the roof of a car, or an antenna that is telescoping that goes out to full length, or something that they can pull up in a tree or hang from a like a curtain rod if they go traveling, because it's a lot more efficient and it allows them to speak further and talk to people that are further away.
Quick question on that, if I could.
Yeah.
So with that handheld radio, how long of an antenna could you connect to that using the same power that's in that handheld to get a better signal out or receive?
You want me to show you a picture? Okay, I took this picture last night. Now, I don't know if anyone can see it. You see that antenna that it's connected to? That's my handheld radio connected to a 3-element Yagi. That is what I used to talk to the International Space Station. It has about 7 decibels of gain.
So the power being submitted from that tiny handheld really doesn't matter. It's all about the antenna.
Yep.
Thank you.
Here you go. That's another photo of me with my station. That's my satellite station. That's what I use to talk to the International Space Station. And I actually did talk to the International Space Station.
Wow.
That's the whole thing. It's that handheld radio connected to a short cable connected to a 3-element Yagi. And yes, those are made of tape measure segments. So, okay, the act of shortening an antenna is known as loading. That's when you make an element shorter, but still electrically the same length. A beam antenna concentrates signals in one direction. So, by the way, if anyone is curious, we are on page 48. It's listed as 48 now. Antenna gain is the increase in signal strength in a specified direction compared to a reference. A Yagi antenna provides lots of gain. That little thing that I was holding is a Yagi. This antenna that you have on your handheld radio, the short, stubby, flexible one, that's known as a rubber duck, and it has very low efficiency. But again, flexible, easy to carry around. Why would you not want to use a radio inside a car? And that's because the car is metal, and metal as a ground plane, if you're outside, is great. If you're inside, it basically traps the signal inside. A 5/8 wave antenna is sometimes used for VHF and UHF mobile. Instead of 19 inches long, it's about 45 inches long. It has a lower radiation pattern, so closer to the horizon even, and it has more gain, but it's also a lot longer. So some people don't like them because sometimes it'll smack against, like, you know, the drive-through when you're driving through McDonald's. All right, feed lines and connectors. So we did a little bit about feed line loss yesterday. So feed line is what is used to get power from one place to another, typically from a transmitter or receiver to an antenna, or from an antenna to a receiver. So here's our antenna up top. Here's our feed line. And here's our receiver and transmitter, or we can call this a transceiver, XCVR, which is a transceiver. It's a transmitter and receiver built into one, and I hate my handwriting. Feed line. There we go. Okay, so feed line is used to connect things together, and it allows you to move power from one place to another. Now, impedance, again, is the resistance of flow of something to AC. So an antenna is going to have impedance as well as radiation resistance. Can everybody hear me okay?
Yeah.
Yes.
Okay,
Yeah, we can hear.
Can't hear.
Yep.
Okay, radiation resistance is what actually causes power to go out into space. It's a part of impedance. Now, ideally, your antenna is going to be 50 ohms. That's going to be the impedance, and it's going to be purely resistive, so that you're basically putting out all your power into space. Now, in order to get that power from the transceiver, which is basically looking for an impedance of 50 ohms, you would typically use coaxial cable, which is 50 ohms. This is a feed line, and it's built like this. Internally, it has a center conductor, and outside, this has a shield, which is usually a braided piece of copper that goes all the way around. Your power goes in this way, your current flows out, and then your current flows back on the shield. So you have two directions. Now, interestingly enough, most of that energy actually flows on the inside of the shield. On the outside of the shield, you have a separate surface because of something called the skin effect, which is completely unrelated to the inside. So essentially you have three surfaces. You have one, you have two on the inside, and you have three on the outside. And that allows us to do all kinds of cool tricks with cable. Basically, this thing called the skin effect, the higher the frequency you go, the more surfacey the current is. Like if I were to draw a piece of copper, like copper wire, at DC, I would have a uniform distribution of current throughout the wire. If I was using AC, I would have almost all the current flowing on the outside. And that's known as the skin effect, and it gets more pronounced the higher the frequency you go. Okay. The unit of impedance is the ohm. Most coaxial cables are 50 ohms. Okay, now, if we were to draw this coaxial cable, we would see that it has a diameter. It has probably some stuff on the inside that's physically separating the inside from the outside, because you don't want them shorting together. And then you also have a length, right? I mean, it has a certain length. It could be 1 foot long, it could be 1,000 feet long, it could be 1,000,000 feet long. So the job of coaxial cable or any feed line is to take power from one place to another. Now, if we were to draw this cable, it actually looks like something. If we have two wires, what does that look like again? What's that thing called? That's called a capacitor. Okay, so I'm going to draw my cable and make it look like this. Okay, and now a wire has a little bit of coiliness to it. What's a coiled wire called?
Inductor.
An inductor. So this is what my cable looks like. And it basically goes on forever until it gets to the end. Now, this is actually kind of interesting because do you see any resistances in there? Are there any resistors?
No.
There are no resistors, just capacitors and inductors. Well, and it turns out that the combination of capacitors and inductors, if I were to put a 50 ohm load here, I could choose my capacitors and inductors so that every time I hit a pair of these, I would get 50 ohms. And if I took another pair, I would have 50 ohms. And all the way at the end, I would have 50 ohms. In other words, it looks like, as far as the transmitter is concerned and the load is concerned, it looks like the cable isn't even there. It basically translates the 50 ohms all the way to the end. And what ends up happening is that the power that I put in goes through this thing all the way to the end, and all of it gets out to the resistor at the end and goes out as either heat or energy or something to that effect. Betty. Alberto.
What page would we be at right now?
Let's see. I don't know that we're on if I had to pick, the page that I would say that we're on is the bottom of page 50.
50.
I also have a really quick question. You said
Yes.
about you have the feed line going up to your antenna.
Yep.
So don't you need to have a ground plane also?
Depends on the antenna.
Okay. In this particular antenna right here.
This one, no. If it's a dipole, then no. It's just 50 ohms.
Okay.
I would just, let's say I built a 50 ohm antenna. Let's say whatever that antenna is. Let's say I built a quarter wave vertical like I did the other day. 19 inches, and these are all 19 inches. I actually built one of these. It's now on somebody's roof. This cost me a total of $5. And
Wow.
it's a 50 ohm quarter wave vertical antenna. 5 pieces of wire and a connector.
Thanks.
Works great. Okay, so that has an impedance of about 50 ohms, and you connect it through this cable, and you get the magical 50 ohms. Now, what we know is that, is there such a thing as perfect wire? Everyone? Is there such
No.
a thing as perfect wire that has no loss at all? The answer is no. So really, there's a little bit of resistance there. And there's a little bit of resistance here because there's no such thing as a perfect dielectric in between things. There's a little bit of leakage of power. So there's a little bit of energy loss in this stuff. Now, the question that I have for you is looking at these conductors that I drew, which one of these do you think, that's a cross section looking at it from the end, which one, number 1 or number 2, is a better conductor?
So number 2.
Why is number 2 a better conductor?
It's smaller.
Well, yeah, but I mean, to me,
Losses are less.
Number 1 would have lower resistance. It's fatter. It's got more area so that it wouldn't burn up as much heat. So number 1 would be the better conductor. So if I were to basically take a cable and I built it like this, here's my center conductor and here's my outer conductor, and I filled the gap with a dielectric, which is an insulator, like that, and the ratio of inside to outside and diameters was exactly the same as this other cable that I built, which had the exact same ratios, where everything is scaled up. Which one do you think is a better cable, number 1 or number 2?
Number 2.
Number 2, because it's physically bigger. There's less resistance and less loss. And in fact, when we go back and we look at, let's say, RG58 versus RG8, these are different forms of 50 ohm cable. And I'm going to bring up a picture. Okay, notice that we have all these different sizes of, if it finally loads. Oh, come on, there we go. Come on. Okay, notice we have all these different sizes of cable. These are all, every single one of them is a 50 ohm cable. They all have that same impedance, and they're all suitable for connecting a transmitter to an antenna. Every single one of them. But they vary in price by a lot. They vary in size. They vary in weight. Why would you pick one over another?
Length.
Because the bigger ones have less resistance.
The bigger ones have less resistance and thus less loss. Right? Now, why would you sometimes not want a really big one?
I'm trying to save weight.
Trying to
Or
save
you-
weight, trying to save money.
Well, you're looking at the amount of attenuation in the power handling capability.
Yep. The bigger it is, the more power you can put through it. But what if you're only going to be running 5 watts versus 1,000 watts? You might be able to
You
get
might
away with
want
the
a
small.
small one.
What if the cable run is only 2 feet long? What if you're trying to slam it in
You'd
your
want a
car
small
door?
one.
What if you're trying to slam it in your car door?
Probably a small one.
Probably a small one. So that's why we basically play this game of all these different cables having a similar impedance, but basically having different purposes. And it's important to know that 50 ohms is a standard for most cable, but not all cables that are 50 ohms are the same. Typically, the bigger the cable, the more power you're going to be able to move through it, the less loss it's going to have. And also, as frequency goes up, your cable loss goes up. So you have to do the calculations. Somebody once asked me, well, I bought a 100-foot piece of cable, and I really don't want to cut it, but I only need 20 feet. What would be the harm? Right? Well, what's the harm in using everything else coiled up on the ground?
Well, now all of a sudden you make a, what is it, a coil?
Well, the coil's okay. The coil doesn't matter. But
It is losses.
yeah, there's
losses
80
because of the
feet. There's 80 extra feet of cable that's just basically getting warm, because cable that has losses, all those losses are turned into heat. So if I have 100 watts of power going out of my transmitter, and I have 80% loss, how much power actually gets to the very end?
20 watts.
And where does the other 80 watts go?
Heat.
It turns into heat. If I really want to heat my cable, that's great, but I typically don't want to do that. I want to put my power out. So if I can cut that cable short and I only have 20% loss now I have 80 watts going out instead of 20, just by cutting the cable. So we told him, cut your cable. Sorry, cut your cable. Buy a new one when you need it. The most common impedance of coaxial cable is 75 ohms. So what happens when the frequency goes up? We looked at this yesterday. I'm going to share this. There we go. What happens when the frequency goes up? Your losses also go up. The difference between RG58 is about the size of a pencil. RG213 is about the thickness of an adult thumb. So RG213 is more expensive, but it also has less loss.
Do the RG numbers correspond to wire gauge?
No, I'm gonna have to try to remember what that is. It's like a radio gauge or something like that. It's just like a military designation of a particular number. Like the sizes go RG174, then 58, then 8X, then 8, then 213, then 214, then 9914. So this is just one of those things that, the more you do, the more you'll know. Oh, radio guide. Thank you, Jared. Radio guide. Okay, which of the following is the lowest loss at VHF and UHF? Notice it says air insulated hardline, and that's because the insulator that's used between the center and the outside is air, which is actually a pretty good insulator. Compared to plastic, it tends to be less loss. Now, the tricky thing with that, of course, is that it tends to be less loss, but air can also get filled with moisture if you don't dry it out. So this is typically used for, like, high power radio and television stations, where your cable, instead of being the size of your thumb, is 3 inches across. Very low loss. They typically fill it with nitrogen to keep it dry. One of the problems with that, again, is that you have to keep it dry. Because one of the worst things that can happen to coaxial cable, typically what kills cable and makes it not work anymore, is moisture. So moisture contamination is the death of cable.
Scott, what about the UV? Does the UV affect the cables as well?
The UV does not directly affect it. So you can have water intrusion, you can have high standing wave ratio, you can have multiple connectors in the line. Every time you add a connector, it adds loss or makes your signal weaker. Moisture contamination is bad, bad, bad. Moisture contamination is one of the worst things that can happen. So the question is, why should the outer jacket of a cable be resistant to ultraviolet light? What does the sun make? Ultraviolet light. What happens to cable when it gets exposed to ultraviolet light? It cracks. What does it always do outside? It rains. Right? So basically you put your cable out in the sun, the jacket cracks, it rains, it gets wet. So once again, it's an indirect way of basically getting water into your cable. And what happens when water gets into a cable?
It doesn't work anymore.
You get corrosion, and it doesn't work anymore. Air core cable is difficult because you have to make sure it stays dry on the inside. A PL259. Okay, a PL259. This is a picture of a PL259. You will get to know these very well. This is a PL259. Everybody see that? That is your classic PL259 connector. The mating connector is called an SO239. A PL259 connector, notice it actually says UHF male. These connectors are terrible for use at UHF. Does everyone remember what the range of frequencies for UHF is?
300 to 3,000.
300 to 3,000 megahertz. These are really good, even though they're called UHF males. They're really good for use at HF and a little bit less at VHF and almost never at UHF. They're terrible for that. For UHF, we typically use a connector called an SMA or an N connector. These are called UHF because before people actually operated UHF frequencies, this was a universal high frequency connector. So that's what UHF stands for in this case. It's called universal high frequency. All right, let's see. Let me go back to right here. PL259 used for HF and VHF. For above 400 megahertz, which puts us into the UHF range, we use type N. What can cause erratic changes in standing wave ratio? That would be a loose connection in the antenna or feed line. And now we are on to standing wave ratio, and as soon as we're done with standing wave ratio, we're going to take a break. Okay, standing wave ratio is a measure of how much energy is flowing out and how much energy is bouncing back and flowing in. Now, the easiest way to think of this is, let's say you take a doorknob on a door. So here's your doorknob. And on this doorknob, you tie a jump rope. And you hold the jump rope. And you take the jump rope and you whip it in your hand when it's tight. And it makes a wave that goes like this, that travels down the rope. What happens when it gets to the doorknob?
It stops.
It does not stop.
Oh.
What happens to it?
Bounces back, but not as strong.
Yeah, a little bit of energy will transfer to the door, right? You might hear the door shake a little bit. But it's not going to be a good transfer of energy. What will happen is the wave will actually create energy that flips over and comes back on the bottom, potentially. And depending on what happens, it might come back on the top. But basically, you're going to have energy going this way. That's your forward energy. And then you're going to have energy coming back, and that's your reflected energy. And why is that? Because of conservation of energy. Energy has to go somewhere. Because basically your energy has to go somewhere, right? And it has nowhere else to go. Now, let me ask another question. Let's take this same jump rope and lay it down on the ground. And we're just going to make it infinitely long. And then we're going to make a wave that is on this jump rope. We're going to whip the jump rope, but it's infinitely long. What's going to happen?
It will just lie flat on the ground.
It'll just but will it ever come back?
Nope.
Nope, it's infinitely long. It will never come back. So you have your power going out and your power going back. This is known as forward, and this is known as your reflected power. Similarly, if I were to take an antenna system, and this is 50 ohms, and my cable is 50 ohms, and my transmitter is 50 ohms, like this, and I put power out, and it goes up, and it gets to this thing that's a 50 ohm antenna. It will radiate power, and none of it will ever come back. It will just disappear into space. You'll never see it again. Now, let's instead take this, and instead of a 50 ohm antenna, we're going to short our cable. What is the impedance of a short? What's the resistance of a short circuit?
Yes.
0 ohms. What happens when our power, which is expecting to get transmitted into a 50 ohm thing, all of a sudden sees a short circuit? That's our doorknob. What's going to happen to the power when it gets there?
It will come back.
It has to go somewhere, so it has to come back. So this would be our forward power, and this would be our reflected power. Now, what happens if I make it an open circuit and I take the antenna away completely? What will happen to the power when it gets there?
It'll.
This is an infinite resistance.
So it won't
Oh.
How much will go out into it?
All of it?
Nothing. Can't. In other words, it's an infinite resistance. Try to push an infinitely hard wall. Right? Try to push a car that has a truck that has its brakes on. That's an infinite resistance as far as you're concerned. You're not making it move. So you get the same result. The power's always coming back. So it doesn't matter whether it's mismatched above or below. Does not matter. Just that it is different from what you're looking for. That will determine whether or not the energy comes back. The degree to which the energy comes back is measured as something called a standing wave ratio. And it is actually a calculation that's performed by values of forward power and reflected power. If all of the energy that's sent out if it all goes out and nothing ever comes back, that's a ratio. That's perfect. That's measured as 1-to-1. Something that is, as your impedance that you're trying to transmit power into gets worse, it could go up to 2-to-1 or 3-to-1 or 4-to-1. And when this number gets higher and higher, your efficiency goes down and down and down and down. In addition to that, this is where you start to get into trouble. Let's say that if I have, let's say 100 watts going out and I have 80 watts coming back, and this is being made by this device. Does that everyone remember what that's called?
Transistor.
That's a transistor. Okay. This transistor operates at, let's say, 36 volts DC. And it's operating at 36 volts DC to make 100 watts. This power that's coming back, what is power? What's the formula for power?
Current times resistance.
Current times voltage. P is equal to I times E. What do you see there? What's that E? What is that?
Energy.
No, it's voltage.
Sorry, voltage. Sorry,
it's voltage. You have voltage coming back. Well, okay, you already were operating at 36 volts. Let's say the transistor above 48 volts will destroy itself. And the voltage that's coming back may or may not be in phase with it. And let's say it's in phase and it's 26 volts. It's going to show up right on that transistor. You have 26 volts DC plus 36 volts DC. What do you get?
56.
You get 62 volts.
Yeah.
You have a maximum operating voltage of
48.
48. What happens to your transistor?
Smoke.
You get smoke. You let the smoke out of your transistor and you destroy your transmitter. So when that happens, basically high SWR can actually kill your equipment. So what we do is we have circuitry that monitors the standing wave ratio. An SWR of 4-to-1, this is a pretty severe mismatch. When the SWR that's monitored gets above a certain point, what will happen is that transmitters will typically sense this and fold back their power. They will reduce their output power to protect the transistors from being destroyed. So that's basically done in most modern equipment. However, handhelds do not do this. If I were to disconnect the antenna completely and then turn it on to high power and key the radio, I would probably fry the transistors in a period of about 5 seconds. And that's why we don't do that.
So this is the practical application of don't run your transmitter without a
Without
antenna.
an antenna, that's right. Okay, so a perfect match is 1-to-1. 4-to-1 is an impedance mismatch. Low SWR means that your signal gets out, so reduced signal loss. Power loss in a feed line gets converted to heat. Why do we fold back the power? To protect the output transistors. Now, a standing wave ratio meter. An SWR meter can only measure, it measures forward and reflected power and calculates standing wave ratio from that. Let's say that a meter is only rated for 200 watts. If you're going to be running 1,000 watts, you probably want a different meter. So frequency and power level. Frequency, they don't always work well at different frequencies. A directional watt meter, if you know how much power is going forward and how much is going reverse, you can use a directional watt meter to measure those and perform the calculation yourself. An RF power meter, which will also usually measure standing wave ratio, should be between the transmitter and the antenna to figure out whether or not you have a good match. An antenna analyzer is a way of putting a small signal out into an antenna and seeing what is happening in the antenna without frying your transmitter. So, antenna analyzer, a great tool. An antenna tuner, we actually saw one of those yesterday. Antenna tuner, again, this will make sense now, looks like this. Where this is the antenna, and that's variable, and that's variable, and that's variable. And we looked at a picture online of one of these that had 2 capacitors and an inductor. And what that allows you to do is take this impedance, which is a big question mark, adjust this, and then adjust this, and then adjust this so that the output looks like 50 ohms. So no matter what's happening out here, it doesn't fix the antenna. If you have a mismatch right here at the antenna, you still have a problem. The power is still going to bounce up and down in this feed line. It's going to, every time it makes that trip, it's going to make the feed line get hot. But what's it going to do to your transmitter? If your transmitter sees that the outside world looks like 50 ohms, your transmitter is going to be really happy and it's not going to fold back its power. And that's why we use something called an antenna tuner.
However, the antenna tuner will absorb the mismatch, and there'll be heat in there.
It can get warm also, yes, depending on the components. Okay, a dummy load. A dummy load is basically a non-inductive wire wound resistor that is 50 ohms. And the reason it's not inductive is because if it's inductive, it's going to have some extra impedance, which you don't want, and it's going to change with frequency. So it's a 50 ohm wire wound resistor with a heat sink, so that when you transmit into it, you can put out your transmitter power into something that just basically converts it into heat without putting your signal out on the air. All right. Everybody,
what would the purpose be for a dummy load?
Dummy load is to basically, let's say you have a 1,000-watt dummy load. Anytime you put a signal out onto the air, it generates interference. It, you got to find a good antenna for it. Is it 50 ohms? I don't know. So if you want to calibrate a transmitter or make adjustments to it, you can, run it into a dummy load, which is guaranteed to be 50 ohms and is suitable for handling 1,000 watts and intentionally converting it into heat, so that you know that you can transmit at full power and not interfere with anyone, and also, transmit into a calibrated impedance. And then you can adjust your transmitter accordingly.
Thanks, Scott.
All right, everyone ready for a 5-minute break?
Yes.
Definitely.
All right, who's got questions? Questions good.
So does the practice exam pretty much cover, like, if you do the practice exam, you would know how prepared you were and what things you would need to study, right?
Yep. I mean, the great thing about it is that this is all the background material that'll make the practice exams understandable if you forget something and understand, why things are. But there are no questions that will show up that you've never seen before.
Okay.
So once we sign up through the link, what happens?
Well, I am wondering if
I just did it. It makes you go to the, is it the FCC website?
Yep.
And you have to register for a certain number that they want. And then you fill that information out on the form to sign up for the exam. And then it takes you to also make the payment and an agreement where you say you're agreeing to all the conditions of the testing, like that you have a computer ready, that you're using a phone for a camera, that you're going to scan your room and you're going to be the only one there and you're not going to, cheat.
Yep. Used to be that you could only do them in person. So the remote exams are in the last 5 years, and pretty cool new thing to be able to
And
do.
actually it's kind of interesting because during COVID I went back to school and it's the exact same process for doing remote proctoring, not real proctoring, but yeah.
Yeah, remote exams and proctored exams remotely and stuff like that.
So is that link good for any day of the week, or or is it just for that Friday?
The one that I sent you guys on the latest one is the one for the Friday exam. But you can sign up for any exam. Let me see. Let's see, where was it? Exam.tools. No, it's not exam tools. Exam study. Remote exams. Anchorage. So upcoming exam sessions. And it doesn't have to be through Anchorage either. If you're a kid, maybe you want to do ARRL because they have a program where if you examine with them, they can actually pay your $35 FCC fee. They can reimburse you for it. But,
so it's not what tools do you have? A calculator, or is it open book? Not open book?
It's a dumb calculator. That's it. And dumb calculator and scratch paper and a pencil. But these are all the exams that are available. Online. Like in the next week. Those are all the scheduled exam sessions online. So if anybody wants to see what those are.
How about in-person testing?
You got to look for in-person testing. You can go to the ARRL website, but that's not going to be inclusive. Check with your local radio club, I would say. A lot of it depends on where you live.
So I'm in a house. I got to scan the house and then.
No, you typically will pick a room. Close the door, say do not disturb, because if anyone disturbs you, you got to start again.
Oh, and they have a camera on monitoring the situation?
2 cameras.
Scott, what state are you from?
I'm in Oregon.
So what it asks for is for you to use your computer that you're on with the Zoom or I think it's a Zoom on it. Maybe it might just be the user interface for the test, and then to use your smartphone. And I think that's what they want you on Zoom. So it uses the camera, and then the phone is kind of recording your activity also.
Yep.
So that
we basically have the phone looking over, or iPad looking from the side, and the webcam looking at you.
So it's just kind of watching that your eyes are looking at the computer, your hands are on the computer, and that you don't have like a cheat sheet or something hidden behind you. And then it'll probably ask you to scan around your room, like you just
Exactly.
turn a circle and show the room so that it shows there's nobody else. You don't have a poster hanging up on the wall or something like that.
A lot of people take their exam in the bathroom. Honestly.
That's funny.
Yeah. Well, it's a small place. It's usually pretty clean, and you know, you can
It'll
you can lock the
probably
door.
it'll probably ask for you to show that your scratch paper is blank
Yep,
and that your
it does.
computer is blank.
Yep.
Or your calculator is blank, and it's kind of just basic. It asks you the questions. It seems really funny at first, but like it's recorded. There really isn't a person there. It's really not that intense. It just is a little bit strange at first to think, what is this thing that I'm doing?
That's cool. That's exactly how it works. That's exactly how we do it. Thank you for that.
Testing at home is not possible. Can I go to the library and they can lock me in one of their little cubicles and monitor me or something?
Sure.
If you go to universities, like typically
Study room somewhere.
Yeah, I know that university and community college libraries typically will proctor exams for you, especially after.
Actually, having a person be the proctor was one of the options.
Yeah, but you typically don't need that. The second, like everyone's got a smartphone, and everyone can go to Zoom. So we do a Zoom session, and it's usually very smooth. It usually runs very, very smoothly.
How many questions and how long does it typically take?
Takes as long as you want it to. 35 questions for the technician, 35 for the general, 50 for the extra. So I know we've had people do the whole thing in 7 minutes. We've had people do the whole thing in 45 minutes. You need 74%, so 26 out of 35. So if you want to gauge how you're doing, take some practice tests after you study all the questions. And when you're consistently scoring over 85%, you're very ready. All right, here we go. We are on to a section that is called, I believe, we did antennas and feed lines, so we are now on to amateur radio signals, modulation and bandwidth and stuff. Okay, so as we showed,
come back later, Scott.
Oh, JD, hey, say hi, JD.
Hi, JD.
So one of our people just gave a very, very good introduction on remote examinations. So you really don't have to talk about very much because everything she said was right about how it's set up, because she went back to school during COVID and all the exams were remote.
Okay.
So she gave the whole thing. But if you've got anyone that you need like information from or anything like that, or want to talk about the process, or look for people who want to go early or late,
I'm going to leave that early late routine up to you.
Okay.
Because you do it so well.
Dennis, no, you cannot administer a test to a relative.
And I got two people that are outstanding right now.
Yeah, I know.
That's one of them. And Yanni was the other. She still owes me an EA.
And I don't have an answer there. So anyway, JD is he's from the Anchorage ARC VEC, and if you've got any kind of spiel to give, JD, by all means.
I'll just toss it out there. Anybody got any questions? Need to know something?
So you're in charge of the test on Friday, and how many spots do you have available?
Well, right now I have 6 VEs and about 15 or 6 leads and 15 VEs. So I'm going to be doing probably 5 at a time. We're going to get about 20 out of here in about 2 hours. So yeah, right now I got 14 slots filled up. I can have up to 25.
Hi, JD. Bonnie
Hi.
here. Hi, I signed up for the class for the Friday test, but I
Uh-huh.
know I will not be able to take the test
Why is that?
because I'm taking the practice test and I am not making even half. So I'm gonna beg out. I want to take it in about 6 months after I get a little more grounded in this information, with this information.
6 months is a long time. You want to
Well,
go 6
I don't
months?
know. I'm kind of slow, so
Yeah, okay.
do you mind? I mean,
No,
I
no,
rather
it's
I
up
let
to
you
don't
you.
know.
mind at
Hey,
all. What, first off, if you do bail out, you don't get a refund according to the policy
that's
of the
fine.
VEC.
Perfect.
The other thing is, if you want to bail out, we'll hold your $15 for 45 days. And if you're ready to go in 45 days, you won't have to pay again.
Okay, well, I could let you know in 40 days. How's that?
That'll work.
Oh, I'll put you on hold then for 40 days, 45 days, and we'll go from there.
Perfect. I don't want to hold the seat up. Thank you.
Okie dokie.
Also, as the question is, when is the next exam that you're going to do?
I mean, there's exams like all the time, every day.
We do exams 6 days a week.
Okay.
And Anchorage
Twice
is
a day.
one of 14 volunteer examiner coordinators.
Got it. I am signed up for Friday's test, but
Good.
I am heading out of town, and a 2-hour limit might mess that up. So
Yeah,
I
you'll be fine.
If it's an hour, then that's what I plan for. But if it's 2 hours, I might have to postpone.
Do you want to go early? We'll get you started.
Tell
at
Scott
the
you want to
beginning.
be one of the first ones to be done, and we'll take care of it.
Yeah.
Well,
All you
that's
need is
enough.
probably about a half hour.
Yeah, I can be available at 8 o'clock if I have to. Specific.
Well, I mean, we would just get you at the beginning.
Oh, okay.
So
10 o'clock then. All right.
And you'll
Chris
probably
has-
be on the road by 10:30.
Yeah. And Chris's hand is up.
I don't see anybody else.
Yeah, so, okay, I was just looking to, where do I find the sign up thing for the Anchorage?
The general sign up, or the specific for what we're doing?
Well, I don't think I'll be ready to test on Friday, but
Okay.
I'd like to jump in maybe the next week after that.
Okay. So I put that out in the chat. Okay, so here is this hamstudy.org. That's all the online sessions. If you specifically select Anchorage, you'll see all the Anchorage exams. But click on that and you'll see there are, 5 or 6 different exams, like literally every day of the week by different VECs. Of course, we want you to go with Anchorage because, why not? But, I like Anchorage.
I just put out the April schedule, and there's 60 slots available there.
All right, we got a lot of stuff left to cover.
If there's no other questions, I got things to do and places to go.
Thank you, JD.
Talk to you later, Scott.
See you later, man.
Y'all, good luck.
Okay, so continuing right along, we are into amateur radio signals, and one of the things that we're talking about with amateur radio signals is that signals, depending on what they're doing, take up bandwidth. Now, if I were to say, I'm going to just whistle, and I'm going to make sure that you guys can hear me whistle, and I'm just going to start whistling and never stop. Okay, now other than the tone that I'm whistling, is there any other information that you can gain out of that? Is there any other information that you can get? The answer is no. How about if I go like this? What information could you gain out of that?
Was that your Morse code?
Well, it wasn't specifically, but how many times did I whistle?
3.
I thought it was 4, but
4.
But okay, and how long did I whistle for each time? About a half a second. And what was the length of the gap in between whistling? Probably a half a second. So there was information there, right? So by taking what's known as a carrier frequency, which is basically just, which is just basically a radio frequency sine wave, by taking that and by doing something with it, we can put information on it. We can make it convey information. That could be just turning it on and off. It can be going like this. By changing its pitch, we can do something. By sending multiple at the same time, we can do things. By turning it on and off for different lengths of time, we can do this, which is Morse code for CQ, which means I'm looking for somebody. That has information on it. That act of changing a carrier by putting information on it, encoding it, is known as modulation. The act of taking it back out is known as demodulation. A box that does that is a modulator, demodulator, or a modem. People who are older may remember the word modem. So what we're doing when we do that is we take signals that contain information and we put them out over a carrier wave on the air. The reason, again, that we do this is because sending no information is kind of boring. So what we can do here is we can go to this web SDR in the Netherlands, and we can go to 14020. Notice it's just one tone, but it's being turned on and off. This is Morse code. We can go to another frequency, and that's shifting frequencies. Here's another one. Different pattern of shifting frequencies. We can also use voice. We can also use a different voice. Now, you'll notice that these signals do not take up very much room. Notice that every one of them is really quite narrow. Morse code does not take up much space. The faster you go, the more room it takes up. Notice that those are splattered a little wider. We can go to digital, which has a higher bandwidth yet. That's another digital mode called PSK. It's actually changing the phase of a signal. This sounds like a player piano. That sounds like a bunch of ghosts. This is FT4. These are frequency shift keying modes. And notice they all take up different amounts of space. This is a single voice signal. What do you notice about that or that?
It's very wide.
To this. Yeah, they're very, very wide. In that same space, I can have about 40 of these signals. I can have probably Morse code signals. I can probably put 15 or 20 of them. That's known as bandwidth. That is how we use up bandwidth. And what this allows us to do is actually display it on a screen. Go ahead, Cooper.
Is Morse code worth learning?
I think so. I use it every day. I love Morse code. I mean, does anyone use it? I use it all the time. I talk to other people. I like it. Do you need to know it?
I'm still trying to learn how to do it, but I have gotten the lessons from Scott.
And I actually recorded my entire last class too that I taught. It was 15 one-hour classes. I have those on YouTube. Okay, so let's look at, here's our center frequency. And we're going to do first AM. AM looks like this. Takes up about 6,000 hertz. FM, frequency modulation, takes up about 10,000 hertz up to 15,000 hertz. That's FM. This is AM. If we knock out the upper and low, the upper, for instance, and the carrier, we just basically end up with this part. This is known as single sideband. This is about 3,000 hertz. We can also have this thing called PSK and Morse code. Like PSK, that's 31 hertz, 63 hertz, 126 hertz, 250 hertz. There's different versions at different speeds. Then we also have Morse code, which is about 150 hertz. So as you can see, different modes, which we just saw on the screen, take up different amounts of space. Now, this is also why, if we look at our band chart, certain modes are not used in certain places. So let's take a look, for instance, at this band chart. And this is, for instance, on this band, let's pick 14.00 megahertz to 14.35 megahertz. If I were to use Morse code, if I were to use Morse code, it would be very, very small on this band. If I were to use FM and it took up 15 kilohertz, it would basically cover, one channel would cover up this much space. That's how much bandwidth one FM signal would take up. Needless to say, we don't use FM there because it takes up too much room. Now, if I were to use FM in a different space, if I were to use FM, for instance, on a different band, and let's go up here, and that same 15 kilohertz, because the band is so much bigger, up here would take up on the 2 meter band about this much room. So it's the exact same signal, but the band is that much bigger because it goes from 144 to 148. And that's why we have the luxury of being able to do FM on certain bands, but not on other bands. Similarly, where our bandwidths are more limited, we can do AM, but AM takes up a lot of room. That's why a lot of people use single sideband. That's why a lot of people use digital modes. Notice this says PSK31, a very narrow mode that we heard. A lot of people use Morse code because you can pack a signal into a very small space. And that makes it more efficient. It makes more efficient use of the spectrum. The spectrum is basically a shared resource for everybody. So, you know, the better you can share it, the better off we all are. Okay, let's see. Type of modulation commonly used for VHF and UHF, that would be FM, which is frequency modulation, where we change the frequency that we're sending, or phase modulation, which kind of looks like FM. For VHF packet radio transmissions, I will turn on my radio and hopefully I will hear something very quickly. This is what packet sounds like. Maybe. But usually it's going to come up pretty quickly. There we go. That was packet. Basically, that is FM radio, but is used for digital communications. And that's from a radio to another radio using a computer. Amplitude modulation, that's basically taking a signal and just the louder you get, the bigger the signal gets. The simplest form of amplitude modulation is single sideband, and that's where we only transmit one sideband. For long distance weak signal contacts, our most popular mode on VHF and UHF is single sideband. The reason that it's not FM is that FM tends to take a lot more space. We can't pack our signals in, and on top of that, if there are two FM signals, because you know, like we were saying yesterday, that AM is kind of like something that's found in nature. Things are amplitude modulated. Things are not frequency modulated in nature. If there are two signals that join together, they typically obliterate each other, and you can't hear either one. On single sideband and AM, you actually can still hear them both. So for weak signal work, where the signals are going to be intentionally weak, because let's say we're bouncing signals off the moon, those are going to be really weak. That would be single sideband. For 10 meters, you have access to the 10 meter band. You also have VHF and UHF. If you're going to be using single sideband by convention, you're going to be using upper sideband. SSB signals, they have a bandwidth of about 3,000 hertz or 3 kilohertz compared to FM, which has between 10 and 15 kilohertz. So that's why for a lot of modes we use SSB. Its main characteristic is that when we're using SSB, it's a narrower band. It's a narrower bandwidth. Again, when using FM, you can only hear one signal at a time. They tend to obliterate each other if there's more than one. The approximate bandwidth of now, old school television. Does anybody watch TV? A TV signal that isn't digital takes 6 megahertz, not kilohertz, 6 megahertz of space. Now, if we were to look at 6 megahertz of space, we would look at, let's say, the 2-meter band. It starts at 144 megahertz and ends at 148. That is not even as wide as a single TV channel. So we only are able to start using TV on this band, which is 70 centimeters. This is approximately from 426 to 432, one television station. We're actually allowed to do that. It's called fast scan TV. On the 33 and 23 centimeter bands, we're also allowed to do fast scan television. And again, those signals are 6 megahertz wide. So like 1240 to 1246 or 1252 to 1258.
What is that?
Fast scan TV. Like your classic old school NTSC fast scan television. Like 30 frames a second. Like TV programming. We're actually allowed to transmit with that. It's called ATV, or amateur television. CW is continuous wave. It's another name for Morse code. CW is basically the act of turning a signal on and off. We turn it on and off based on Morse code and what we know the letters to be. Of these 4 modes, CW has the narrowest bandwidth of about 150 hertz. And finally, an electronic keyer is a device that sends DITs and DAWs automatically, depending on whether you press one button or another. And it allows you to send Morse code electronically. Allows you to send it faster. All right, now we're into digital modes. All right, what makes digital different from anything else is that digital is computer communications, ones and zeros. So packet radio, that's how radios talk to each other, like I just heard that little squawk on my handheld. 802.11 we know as Wi-Fi. FT8 is a digital mode that allows you to communicate with very, very low, weak signals, like we were actually listening to on that web SDR. Packet radio, the way that a packet works is that you basically have a message and then you have an automatic repeat request, which basically says, I didn't get the message, please resend it. And it also contains a checksum. So for instance, if I have a word that has these that is this 1011010, that has 1, 2, 3, 4 values of 1. Those are binary. There's an even number, so you would add a 0 to the end of it. That's known as a checksum. It's a very simple way of figuring out whether there was an error, because if this number ended up coming in, well, okay, 1, 2, 3. This one should be a 1, but it's a 0, so obviously there's a mistake. So the checksum basically said, oh, I have an error, and I'm going to send a message which says ARQ, automatic request, please. Automatic repeat.
How did you know there's an error in that count? How did you see that there was an error?
Yeah, there's an error in that count because let's say that the number again was 1011010. That's the word. You count even bits, 1, 2, 3, 4. It's an even number, so you would add a 0 to it. And let's say that this went through the channel being transmitted, and this was what was received, 1001010. something got corrupted on the way. You don't know which one got corrupted, right? But you do know that if it was an even number, you add a 0, which is even, and the total should be even. If it was an odd number, and then you added an odd number to it, what's an odd number and an odd number? It's even, right? Either way, when you receive something, you should have an even number of ones. Now we're going to count them, and we get 1, 2, 3. That's an invalid word. So at that point, you say, please ARQ, automatic request for a repeat. I need a repeat. Because obviously what I got doesn't make any sense. And that's known as a checksum. And this is a very basic form of error detection. Uh-oh, I heard somebody. Nope, okay. APRS, the automated packet reporting system, or automated position reporting system. APRS is a method by which we combine packet radio and ham radio and GPS to provide real-time tactical information on a map. So what can you send? Position data, text messages, you can send speed, you can send weather data. So for instance, let's say that I wanted to share, let's say that I wanted to, oh heck, where'd it go? I want to close that. Let's say that I wanted to send some information about where I was going on my trip. So I turned on my packet transmitter and I went to aprs.fi, and this is the map of everybody who is sending out information in the entire Willamette Valley. So, oh look, you see that trail right there? That is somebody's track. It's K7 or KJ7T-9. And we can look at how fast they were going and where they went and when they went, and that was the path that they took. Now, whether or not they were going off-road, I have no idea. They might have been flying. The information would basically tell us if you looked a little deeper into it. So this is around Portland. Oh, there's somebody's trip. All of these WXs are weather stations. And basically all you need to set something like this up is a radio capable of APRS, which is a form of packet radio, and a global positioning system receiver. Some radios actually have them built in already, in which case you basically just turn it on and you're good to go. Okay, other stuff. So that's APRS.
So that weather capable radio, does that need to be tied into a weather station then?
Yeah. Yeah, if you have weather information, and it could be from your computer too. I mean, there's all kinds of cool stuff to do as far as combining technologies here. I mean, it's all just digital data at some point. You know, if you want to write an interface to combine, you know, data that's coming in from your computerized weather station and forward it to your radio, you can do that. You know, you just have to write it, or somebody else has already written it and you just have to use it. PSK is phase shift keying. DMR is digital mobile radio. This allows 2 digital voice signals. So you're basically, when you make a phone call and you speak, that's an analog signal. At some point it gets sampled and turns into ones and zeros. Those ones and zeros then get transmitted over the phone lines through the internet as ones and zeros. Similarly, if you have a digital mobile radio system, you speak into your radio, there's an analog to digital converter that converts your voice into ones and zeros and then sends digital signals over a single repeater channel. So you can actually have 2 different signals at the same time going through a single repeater. And that's known as DMR. WSJTX, That's used for weak signal, meteor scatter, and Earth, Moon, Earth. When we heard those signals going over the web SDR, those were typically being sent by WSJTX software. The most common mode that's used there is known as FT8, which is a very, very low signal to noise ratio mode. And it was actually designed for use when talking to the moon, bouncing signals off the moon. And it also turns out that it's really, really good because it's useful for, things as far off as talking to the moon. You can actually really easily use it on the Earth as well. A mesh network, there's something called ARDN, AREDN, which is the Amateur Radio Emergency Data Network. And this is the process of creating a mesh of Wi-Fi routers, like ubiquity routers, repurposing them through changing the firmware so that they actually can communicate over the ham radio bands, which actually are shared with those frequencies. So Wi-Fi frequencies and ham radio frequencies typically overlap. What's cool about that is that there's a lot of commercial equipment out there. What's really cool about it is that now you can put a call sign on it and up your power and up your antennas and transmit, Wi-Fi over a distance of 30 miles, which is really nice because if the internet goes down, you still have, a Wi-Fi system. Okay, station safety. Okay, this is we're going to go through this pretty quick. Most of it is common sense. What health hazard is presented by electrical current flowing through the body? It can cause heating of tissues, disrupt electrical function of cells, and cause muscle contractions. Just out of curiosity, has anyone ever gotten a nice shock in their life?
Yeah.
Yeah, it doesn't feel good, does it?
Once by plugging in a computer cord.
Did your finger touch one of the hot wires?
Probably.
Yeah. I once got a shock from a 250 volt DC transformer. My arm started here and ended up here, and I didn't have anything to do with it. Okay, in the United States, there are 3 colors inside a power cord. They're black, white, and green. Black is the hot wire. White is neutral, green is ground. So black is the hot wire, white is neutral, green is ground. If you're going to be building a station, use 3 wire cords. Black is hot, white is neutral, green is ground. Connect everything to a common safety ground and install mechanical interlocks and high voltage circuits. If you are going to get a tube amplifier, you might have as much as 3,000 volts floating around in there. Every so often, somebody dies because they stick their hand into a box where there's high voltage, because they basically eliminated the safety interlock and then killed themselves. So don't do that. A fuse in an electrical circuit removes power in case of overload. A fuse should be installed in the in series with the hot conductor. And what color is the hot wire? Everybody remember? Black wire.
Black.
Yes. So fuse or circuit breaker goes in series with the hot wire. Why should a 5 amp fuse never be replaced with a 20 amp fuse? Well, we talked about this briefly yesterday. All of a sudden, your wires are carrying too much current. They get hot and they burn your house down. What hazard exists in a power supply after turning it off? If you have a filter capacitor, it gets charged up. And what happens if there's no way to discharge it? You might have an 800 volt capacitor that's got 800 volts on it, and you stick your hand in and you get a nice 800 volt shock. So filter capacitors can store massive amounts of charge and can discharge it through you.
Is there a safe way to remove that before you?
If you know it's there, you measure it, and typically what you would do is you just put a resistor across it, a bleeder resistor.
Yeah, if you're
fixing an old TV, were you going to say?
Oh, I just didn't want to talk on somebody. Yeah, if you're fixing your microwave and have that open, there's a very large capacitor inside, and the instructions, if you read them, says use a screwdriver to short across the terminals of the capacitor before you reach in there, because it can kill you.
Yep. Okay, you also need to take precautions when using batteries. Uh-oh. Cooper's got apparently Cooper found the annotation. Hi, Cooper.
I didn't mean.
Which of the following is a safety hazard of a 12-volt storage battery? What makes a 12-volt storage battery? What's inside it, everyone? Who knows?
Acid?
Yeah, it's lead and sulfuric acid. So, if you overcharge or discharge a battery, like a car battery, it generates hydrogen gas. And hydrogen gas, if there's a spark, can blow up. And just to be lucky, if it happens to blow up and the battery is full of sulfuric acid, guess where all the sulfuric acid goes?
On your face.
It goes all over your face. So yeah, typically that's a really bad day. So if you're using a 12-volt storage battery, that's why whenever you're whenever you're jump starting a car, it's very important to do it in the right way to keep the spark away from the battery. You don't want to blow a battery up. That'd be a very bad day. So a battery that's overcharged can outgas. That's a bad thing because it's hydrogen. Okay, antenna and tower safety. When putting up an antenna tower, it's always important to look for any overhead wires. Overhead wires. Does anybody know what the overhead power lines are? They're in everybody's neighborhood, right? Everyone's seen a power pole, right? And it has a cross arm that goes like this. And there's something that goes like this and like this and like this. And there's a wire that goes like that and another one that goes like that and another one that goes like that. And maybe there's another one that's the ground wire that goes up above. Right? Everybody's seen those, right? What
They're
voltage?
all over my neighborhood.
Yeah, okay. What voltage is up there?
Usually in residential, it's 64,000 volts.
Yep. I've seen a lot of 12,400. You can also have something on the order of 30,000. You can also have 60,000 volts. All right. Now, when you get to your house, that's 120 volts, and it usually comes in as 240. So, how does that voltage get converted?
Transformer?
Transformer. A transformer that connects here, here, and here, and generates power that comes out at low voltage over here. The reason this is done is because power is power, and P equals I times E. And so if you can raise the voltage, you can lower the current. And because E is equal to I times R, and P is equal to I squared R, the amount of power that you lose in your power lines is proportional to the current squared. Makes a really big difference. So that's why the power company likes to transmit power at really high voltages. Even in your neighborhood, something like 12,000 volts or 60,000 volts, because anything above, 480 volts is going to kill you anyway. So, what's the difference, right? So just when you're putting up an antenna, make sure that that antenna is not going to fall to anywhere within at least 10 feet of those power lines. At least. And typically, I would go even further away.
Scott, why is it better to be at extremely high voltage?
Well, the higher the voltage, what's the formula for power again?
E times I times E.
I times E. Okay, so if you can raise the voltage to get the same power, what do you do with the current?
It reduces.
Reduces the current. And power loss in a resistor is I squared R. And your wire is a resistor. So if your power goes up, your losses that heat your cables go up drastically. So the higher the voltage you can transmit it at, the much lower the current, which means you lose a lot less power in your power lines.
It's cheaper to do it that way?
Oh yeah, I mean you're not getting money for it, right? If you burn it up as heat, you can't sell it to the customer. And if the wires don't get hot, then they don't catch fire or melt. So you just have to make sure that, the spacing is such that nothing's going to touch it. That's why, in California, that's why condors would get electrocuted, because their wingspan is big enough that they would actually touch two power lines at the same time. and get electrocuted. And that's why in California they've actually increased the spacing on power lines so that the birds don't touch two wires at the same time.
When power companies are transmitting long distances, hundreds of miles, they'll usually change to a DC power line rather than AC because there are fewer losses.
And it's only two wires. Now it can be a little challenging to create 1,000,000 volts DC, but that's how they do it. You can also have 750,000 or 1,000,000 volts AC, 3-phase, over long distances as well. But yeah, that's why when they go from a power generating station, they go up to at least 345,000 volts, because you can transmit massive amounts of power that way with very low current. Okay, when putting up an antenna tower, again, look for and stay clear of wires. The minimum safe distance is 10 feet. You have to be at least 10 feet away if any part of the thing falls. Why should you avoid attaching an antenna to a utility pole? Because there are high voltage power lines up there. Number 2, you don't own them anyway. So probably not a good idea to climb up there. When touching an antenna that's transmitting, you can get an RF burn, which makes a little pinhole in your skin. It hurts a lot. So don't touch a transmitting antenna. When climbing a tower, you have to be trained in tower climbing. You have to be good at it. Tie yourself off to the tower at all times and wear an approved climbing harness. I know people who occasionally will fall off of towers and die. Right? This is usually a bad thing. The other thing is, when is it safe to climb a tower by yourself? Even if it's just a little bit of work that needs to be done. Well, if you have a heart attack or you trip and like sprain something, you are stuck. If you get stung by a bee, there is nobody there to help you. So you never climb by yourself. When using a crank-up tower, which is something that literally has a crank and extends, you either put locking mechanisms in place or you retract it completely before climbing it. A turnbuckle through a guy wire. A turnbuckle is something that you use to screw. It's basically a screw that pulls tension on a rope that's used to make sure that a tower doesn't fall down. When wind blows through a tower, it'll vibrate and it'll tend to loosen the guy wires. So we use a safety wire to go through it to make sure that doesn't come loose. When grounding is really important. You follow local electrical codes. In order to ground a tower, for each tower leg, if you have a 3-leg tower, you ground each leg to an 8-foot ground rod, and then you ground those to each other in a ring. When installing ground wires on a tower for lightning protection, you want short and direct connections, and you want to avoid sharp bends because lightning does not go around sharp bends. It would rather jump away from a wire and make a jump to the ground than go around a bend. External ground rods need to be bonded together with heavy wire or conductive strap. A lightning arrestor is basically a tube that goes in line with your cable. So here's your cable, and it's a tube that has a ground. Notice this little ground, and internally is the center conductor, and it comes to cable on the outside. And this actually has a gas-filled tube that usually can handle thousands and thousands of watts of power without doing anything. But if there's a lightning strike, this could be as much as 20,000 volts, which is enough to take what's in that tube and make it turn into basically turn it conductive. And what will happen is it will turn into an ionized gas, and this will be a conductive path. And hopefully this will short the lightning strike to ground. And if your radio is inside, hopefully your radio does not blow up. What's the safest thing to do if you know there's a thunderstorm coming? Everyone?
Unplug your radio.
Unplug everything and disconnect all the antennas. I remember being out on field day once and there was a thunderstorm coming. We disconnected everything because we knew there was a thunderstorm coming and it wasn't even raining yet. and I heard zap, 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 zap. That was the sound of, here's our PL259 connector, and here's the center conductor that went into the radio. That was the sound of lightning and static, really just static electricity, jumping from the center conductor to the ground. And that's, 20,000 volts. That was just coming down from the antenna. Wasn't even connected to anything. Zap, 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 zap. Okay. Where should all of your lightning arresters be installed? On a grounded panel near where feed lines enter the building, so you can run it straight down to the ground.
Wait, so if you touch that, would you have died?
No, there's no current behind it. There's a lot of voltage, it would hurt, but there's no current behind it. And what kills you is current. About 10 milliamps through your body, if it goes through your heart, is enough to stop your heart. That's not a lot of current.
Yeah, I heard an electrician once ranting about how high voltage lines should be labeled high amperage lines, but no one can understand it.
Well, it's both. Yeah. But I mean, a 9-volt battery in theory can kill you if it finds a good path, right? Fortunately, your skin is a fairly good resistor. It doesn't tend to, even though we're filled mostly with salt water, which is a good conductor, our skin is very resistive. If you ever want to try an experiment, take a voltmeter, grab both leads in your hands and watch what happens, and then lick your fingers and do it again, and you'll see that the resistance gets lower. Okay, RF hazards. We are into RF hazards. RF hazards can be, they exist. You can hurt somebody. That's why we're in class. Radio waves are non-ionizing radiation, which means that unlike X-rays, they don't have enough energy in the photons to rip apart your atoms and make you mutate and get cancer. So that's known as non-ionizing radiation. However, as we know, there is enough energy, because of microwave ovens, in radio frequency energy to cause heating. So not enough damage to cause changes in cells or damage DNA, but certainly enough to cause heating. Who is responsible for ensuring that no person is exposed to RF energy above legal and safe limits? That would be the station licensee. That is you, right? That is you. If you are 8 years old and you have a handheld radio, you are the station licensee if you have a ham radio license. And it's up to you to make sure that nobody is exposed. So it's actually a pretty big responsibility. The easiest way to verify this, you can go through all kinds of mathematical calculations. You can take field strength studies. However, the easy way to do it is that we go to hint link, power density, and somebody has taken the really complicated FCC document and done everybody a solid by taking it and making a web-based calculator out of it. So you can say I'm transmitting at 20 watts average, and notice antenna gain in dBi, that's compared to an isotropic. But normally we do dipoles, so we're just going to use a dipole, 2.2. Compared to a dipole, compared to an isotropic, we're 10 meters away from it, and we're at 144 megahertz, and go. Okay, so you take this, and you print this out, and is it safe? Here's your power density in milliwatts per square centimeter. That's like an RF flux. You have your maximum exposure limit for a controlled environment, which basically means that the general public isn't walking through. An uncontrolled environment means that the general public who doesn't know what's going on is just allowed to walk through. Notice that the limit is a lot lower. But this basically says that at that power level, the general public can come to within 6 feet of your antenna and still be safe. So you take this, you print it out, you put it on your wall. If anybody asks, you know that you have a safe station. And again, it's done so that somebody can very easily go through there. And that's what I use. I don't go through all the other performance. I don't go through all the other stuff. I just go through the calculations. It's a worst case scenario kind of calculator. Duty cycle. That is the percentage of time that a transmitter is transmitting. So if I am transmitting for 1 second and not transmitting for 9, that would be 1 out of 10. That would be a 10% duty cycle. The duty cycle allows you to calculate the average exposure to radiation. So if I'm transmitting 100 watts for 1 second and then nothing for 9 seconds, that would be 100 watts for 10% of the time, and 10% of 100 is 10 watts. So my average is 10 watts. Similarly, if I change my duty cycle from 100% to 50%, that means that I can transmit twice as much power when I'm transmitting to get the same effect. RF limits, exposure limits vary with frequency because the human body, as we know, is basically a bag of salt water. Salt water is conductive. We absorb RF energy. We absorb different levels of energy at some frequencies than others. And that's why they vary. And it turns out that the highest absorption level occurs at the 50 megahertz band, which is 6 meters. So the maximum permissible exposure is lowest because we absorb the most at 50 megahertz. If you have, for instance, an antenna that looks like this, how much energy is there going to be down here on the ground? If most of your signal is going out this way, how much energy, and this is on a big tower, how much energy is going to be down on the ground?
Very little.
Right, very little. Now, if I were to take this antenna and instead move it so that this antenna was a vertical antenna which was mounted on the ground like this, how about now?
There would be a lot on the ground.
Really close to it. So the position of the antenna and the radiation pattern and what it looks like makes a very, it has a very significant impact on how much exposure you're going to have. So if it turns out that, for instance, like over at the museum, the Eugene Science Center, we have a station, we go in through our calculations and everything is safe, but let's say that somebody does a calculation and they come up with new numbers and find out that it's not safe. Well, we can move antennas and then do the calculations again. We could also make it so that we don't transmit on a certain frequency where it's particularly bad, or we can reduce the power. All these things play into the calculations. And finally, if you buy a new transmitter or you build a new antenna, you should go through the process again. And you just have to run the calculations again. And fortunately, somebody has come up with that really cool little calculator, which I put a link for out there. And you just do it again. All right, station setup and operating controls. Okay, so now we're going to talk about how we connect stuff to other stuff. So here's our power supply. And what voltage is our power supply going to usually operate at for a mobile radio?
120.
Well, it's 120 volts in.
12 volt? Oh.
And the output is at 12 volts DC. Okay, so let's say that our mobile radio is a 100 watt output. 100 watts at 12 volts, what would that be? P equals E times I, right? Which would be 12 volts times I, and we know that's 100 watts. So PIE, we don't know our current. I is equal to P divided by E, which is 100 divided by 12, which is about 8 amps. Does that sound right? Well, the problem there is that our efficiency is somewhere on the order of 40%. So to get 100 watts out, we really are only at 40%. So 40% is equal to 100 watts over something. And that actually is about 250 watts. So as it turns out, typically, in order to run this radio, we need about 20 amps. Okay, so now what we're going to do is say, okay, we're going to run this 20 amp cable, and this cable is going to have a resistance of about 1 ohm. How did I get that efficiency? That's just the way things work. You have to, basically, that's the conversion efficiency of a typical transmitter, 40 to 50%. Okay, so now we have 20 amps going through a 1 ohm resistor. That cable has a resistance of 1 ohm. All right, let's go through our calculations. E equals I times R. Okay, we have our E, which we don't know. I is 20 and R is 1. How many volts do we lose?
20 volts.
20 volts. What did we start with?
12 volts.
12 volts. What will happen? What's going to happen?
It's not going to work.
It's not going to work at all. You're going to have no voltage left to run the radio. So what we can do is we can say, okay, let's make this resistance 0.1 ohms. So now we have 20 times 0.1, and we are at 2 volts of drop. Well, if we had 12 to start, now we have 10 volts left. Yeah, it's okay, kind of. Not really. Okay, well, we need to have an even lower resistance. Let's go 0.05. Now we have 1 volt of drop, and now we have 11 volts here, which is better. We could probably get away with it. So now the question is, how do we make this resistance lower and lower and lower? What do we do with our wires?
Go up in diameter.
Go up in diameter and?
Make them shorter.
Make them short. So we want our power connection cables to be short and fat. We want the biggest cables we can get away with, and we want them to be direct and short. And you know, I tell people that 90% of problems are solved by Ohm's law. This is even true in my job. 90% of problems are solved by Ohm's law. Okay, the typical rating for a 50-watt transmitter, in order to make 50 watts, you actually probably need about 120. So I would go for this 13.8 volts at 12 amps. In order to interface a computer to a radio, well, you have a radio that has a speaker output, it has a microphone input, and it has something called a push-to-talk line. The button on the side of a radio is the push-to-talk line, right there, push-to-talk. So you basically, if you're using a computer, you need something to key the radio. So the computer is going to have to be listening to what's coming out of the radio. So the microphone of the computer, the sound in, is going to have to connect to the radio's output, or the speaker. And then the computer's speaker output is going to connect to the radio's input. And then it's just going to have to take a line which will short out the push-to-talk button. So in order to do that, you need receive audio, transmit audio, and transmitter keying. That basically turns the transmitter on. Similarly, if you're using FT8, why would you do that? You would take the audio being generated by the computer using this software and pump it into the radio so you can do something with it. All right. Computer line in. Go ahead.
What would be an example of the WSJTX software?
That actually is here, WSJTX. Here we go. This is one of the many software packages that exist for amateur radio. And this was actually written by this guy.
Is it just for messaging, or can you run data equipment with it?
Whatever you want. Whatever you want to do with the data. So this guy right here, notice JT, Joseph Taylor. He was the founder of WSJTX. And anybody ever heard of him? He's K1. He's K1 JT. He's also got a Nobel Prize in physics. So he's a ham radio operator. On the air, we know him as Joe. If you send him an email, he answers Joe. He also happens to have a PhD in physics and a Nobel Prize. So, you know, just
Awesome.
one of those ways that, you know, ham radio is kind of like the great equalizer of people. You know, we're all in this together. It's a common hobby. And he took that software package and made it available to the world. And I would say probably now 50% of the contacts made on the air are using his software, which he gave to the world for free. If you have RF current on the shield of a microphone cable, you will get distortion. This is a good time to talk about ferrites. Okay, so any piece of wire can carry RF. If RF is flowing as current, current makes a magnetic field. Now, how to get rid of this? You can take, again, a donut-shaped thing, which is basically like a core that looks like this. And this is a solid donut. And it is hollow. And it's basically a combination of iron and nickel and cobalt and a few other things and glue, all baked into a nice little donut. And you take your cable and you run it through it, and sometimes you might wrap it around it a few times and then pass it out. And what happens is that the magnetic field that is generated by the RF that's flowing on that cable will be caused to circulate around this core, just like in a transformer, except that there's nothing to transform to. The selection of metals that you've picked is such that it will tend to respond to certain frequencies. Those frequencies, if it happens to be really lossy at those frequencies, will basically cause that magnetic field energy to circulate around and around and get burned off as heat. And if the energy is burned off, how much of it comes through the other side?
Nothing.
Bye-bye problem. That's known as choking of a signal. And that's an RF choke, or radio frequency choke. We use those all over the place. Sometimes we use them as transformers. Sometimes we use them to effectively end a cable. Now, interestingly, one thing about cables is that, let's say that we have our piece of coax here, which is coaxial cable. Here's our center conductor. Here's our shield. We have an inside of the shield and an outside of the shield. These are actually three surfaces. You have 1 and 2 and 3. This is because of that thing called the skin effect. Because RF energy travels on the surface of a cable. You actually have two surfaces of that shield. You have the inside surface and the outside surface. What is outside the shield is actually physically separate from what's inside. It's electrically separate as well. So you can take this cable and you can put a ferrite choke on it. That will have no impact at all on what's inside, but anything that's flowing on the outside will be affected by it. The inside is like its own little world. The outside is what's physically outside it. So this ferrite choke, if there's energy flowing on the outside, will suck up what's on the outside.
That should be around 2 inches from the end, right?
Oh, it could be anywhere. Depends on what you're building.
Okay.
Sometimes this is actually at a specified point. So let's say that you have a cable that goes like this. And then it bends and goes inside. And then there's another conductor that comes up from the center. This is actually called a coaxial dipole. And it takes advantage of this right here. The inside is connected basically to the outside, so that you then put a choke right here. And that allows RF energy to flow down the outside until it gets to here. And then you now have the one half of the dipole, which is a quarter wave long, and the other half of the dipole, which is a quarter wave long. And guess what you have? A
Antenna.
single piece of cable with the other half of with the conductor as the other half of the antenna. And that's known as a coaxial dipole. And the key to a coaxial dipole is the choke right here at a very specific point.
So you could do that with RG58.
Yep.
Make an antenna out of that, huh?
Yep. Pretty cool little trick. Okay, next. Which of the following conductors is preferred for bonding at RF? That would be a flat copper strap. The reason being that of that skin effect again, if you're looking to maximize surface area, pounding a cable flat maximizes the surface area. So it minimizes the resistance to RF. If you're connecting a radio to your car, you want to go directly to the battery. The reason being that if you look at how a car is built, it uses all the body panels as a common ground. Those common grounds are not necessarily designed to handle 20 amps of current flowing back from a radio. So you don't want to rely on those welds to handle 20 amps. You want to go straight back to the battery. How do you determine the length of time an equipment can be powered from a battery? Well, batteries have this thing called an ampere hour rating. Amps are current, hours are time. Well, an amp times time is a capacity. In other words, I can deliver, let's say, a 20 ampere hour battery. I can deliver 20 amps for 1 hour, or 1 amp for 20 hours, or anywhere in between. So you divide the ampere hour rating by the average current draw, and that'll give you the time. Okay, operating controls. Excessive microphone gain. This is excessive microphone gain. Right? Basically, I get distorted when there's too much audio. It basically drives the transmitter into nonlinearity, and I sound distorted. Now, we're also going to pull up WebSDR again, because this is a really good way to see what happens with filtering and all other cool stuff like that. And fortunately, over on this particular SDR, there's always something going on. Can everybody hear it? Is the audio coming through? Yeah,
Yep.
okay.
It starts to come through, but then I think your filtering stopped.
But okay, can you hear this though?
Yes.
Okay. All right, we're gonna pick a less noisy one. There we go. There we go. Okay, so now we're going to pick the wrong sideband. Can't understand anything, right? Speech is inverted. So if we have the wrong sideband picked, that's what it sounds like. Now here's the other thing. We can narrow this down. This is basically narrowing down the received performance of the receiver. Notice what happens when we do that. Can we understand what the person's saying? I can't. But can we use that same thing to listen to Morse code? His name is Nasco. Okay, so basically what we've done is we've used different filter bandwidths to realize that certain signals require different amounts of bandwidth. They take up different bandwidths, and they have different filters that allow you to listen to them. So if you're over modulating, that means you're putting too much power into your voice, and it's overdriving the transmitter. If you are above or below a signal's frequency, you'll get distortion, which we heard. You're on the wrong sideband, or you're above or below. It'll sound like Donald Duck or Mickey Mouse. Or the tuning knob that we have is called a VFO knob, or variable frequency oscillator. This goes back to the day where we have a knob to tune the radio that would actually change the look of a capacitor. It was literally a variable frequency oscillator. We also, in a lot of cases, have a keypad like I was using to directly enter the frequency. Most radios today have memory channels. This little handheld radio has, I believe, 1,000 memory channels just in a little handheld radio because it's just a computer. Scanning function of an FM transceiver allows you to basically scan through a bunch of frequencies to look for stuff that's happening. If I turn this radio on, I usually turn the squelch up, put it on memory, and just scan through the memories and let it do that for hours on end.
So,
yes.
A couple of, must have been a year and a half, 2 years ago, there was a lot of talk about the Baofeng radios that they were going to restrict the frequencies that they could transmit and receive on. And can you briefly explain that?
Well,
and the desire to have them?
Okay, so what are the rules regarding amateur coverage? Part 97. Business band is Part 90. Users, commercial, like CB and stuff like that, those are Part 95. A radio has to be, in order to be legal to be used for a certain service, it has to be type accepted for use in that service. Part 97, there is no specific type acceptance because we're allowed to build our own stuff. But if you're going to be using the business band, it has to be accepted for Part 90. If it's going to be used for FRS, GMRS, and things like that, it has to be Part 95. There are very specific rules in the FCC documentation regarding power outputs and signal purity and stuff like that. The ability to change frequencies, they call it frequency agility, directly from the keypad. Baofengs were not designed with any of those in mind and did not meet either Part 90 or Part 95. They were only designed for Part 97, which can only be used by hams. We are allowed to tune those. We're allowed to tune radios anywhere we want. We're not allowed to transmit outside of the ham bands. Those radios would transmit on frequencies that were covered by Part 90 and Part 95. And as a result, were completely illegal for sale in the United States. And that's why they got into a lot of trouble for it.
Yeah, there are a lot of people up in Canada that they are not happy with their Baofengs.
Yeah. But I mean, that's why they're no longer legal for, that's why those ones that were open are no longer legal for sale. Got into a lot of trouble for that. Okay. Go ahead. Oh, I thought I heard a question.
Yeah, I was going to say, what's your opinion about the what's called that Signal Link USB?
Oh, Signal Link is a great little box. I have 3 of them.
Yeah, I got one. I installed it, but I haven't connected it to a laptop yet.
Oh yeah, Signal Link is an external. It's an external sound card for anyone who doesn't know. It's an external sound card for a radio that doesn't have a sound card built in. It's basically for interfacing the push to talk and the audio back and forth. It's about $100 new, and they work great. They can turn any radio into a digital capable radio for $100.
I have the 802.
Yeah.
Yeah, I got an 802 on the boat, and I was told then I bought this one to hook it up to the laptop so I can have the frequencies on the laptop transferred.
Yep. Okay, let's see. Another one is, we have this. This is called squelch. Everybody hear that annoying sound? That is squelch open. This is squelch closed. Squelch is designed to basically eliminate a receiver's audio when there's nothing to listen to. Okay, now we're into repeaters. Repeater offset. So when I transmit using a handheld radio, and I have a transmitter right here with an antenna, and there's a repeater up on top of a mountaintop. The repeater will be published to be operating at 146.72 megahertz, for instance. That is the output frequency. Now, the repeater automatically retransmits everything that it hears on 146.12 megahertz, which means that in order for my signal to get received, I have to switch the radio's frequency from receiving on 146.72 to transmitting on 146.12. That is known as the offset. Now, at the same time, I also might have a PL tone or CTCSS or digital code squelch tone that I have to transmit along with it. Those are basically keys. They're either subaudible tones or a digital frequency shifting pattern that the receiver controller over here has to pick up. If it sees that I am not meeting any of those required protocols that it's looking for, it will not retransmit my signal. So those are basically like keys to access the repeater. So if you're on the right frequency and you can't get, and you don't hear the repeater acknowledge your signal, that means that one of these is probably not set right. It could also be that your offset is wrong, or offset, depending on what frequency you are, could be positive 600 kilohertz on the 2 meter band, or negative 600 kilohertz. You could have the wrong one selected. That is determined by the part of the band that you're on, whether it's plus or minus. On the 70 centimeter band, it's plus or minus 5 megahertz, depending on the section of the band that you're on. So that's 70 centimeters. And this is 2 meters. That's basically how a repeater works. Okay, let's see. That's repeater offset. A digital hotspot, that's communicating using digital voice or data systems via the internet. A transceiver and a digital hotspot. A talk group on a digital repeater. Digital repeater is something like DMR, digital mobile radio, which allows multiple groups to share a single channel without hearing each other. And that uses a time slice. So group A gets slice 1 half the time. Group B gets slice 2 half the time. Your radio is synchronized to the repeater's time base, and you get to transmit on in the A period of time and the B period of time. And when you're not using it, your receiver just basically turns off. So that's again known as a talk group. You have to program your radio with a group's ID or code. Now, interestingly, there's also a lot of connection with the internet. A lot of repeaters, including like ours here in Eugene, we have an internet link which allows people to connect to our repeater over the internet. There's also, when you look at your programming of your radio, there's something called a code plug. This determines how your radio accesses repeaters and talk groups. Similarly, going the other way, there's something called Echo Link, which allows people on the internet to access a remote repeater. This is how, for instance, if I'm traveling around the world in a place where obviously I'm too far away from our repeater to use it, and I want to talk to some friends over the repeater during a net, I can use my phone that has internet through Wi-Fi and connect to my local repeater and act as though I'm standing right here at home. Okay, a DMR code plug has access information for repeaters and talk groups. A specific group of stations selected, you have a group's identification code. A26. Okay, if everybody who wants to use that is on A26 and all the people who are using A26 are connected to the same talk group, then all the repeaters that use it could be going through the internet, and all those people on handheld radios could be thousands of miles away talking over their handheld radios to each other. Color code. Color code is something that has to, color code is another one of those things that's sort of like a channel. So you might be red code or blue code, and it must match the repeater color code to access the repeater. D-Star is an ICOM and Kenwood specific digital mode for voice. So if you use a D-Star radio, that basically means that there's additional information transmitted along with your signal, which will contain your call sign. So you have to put your call sign into the radio. If you have a multi-mode receiver or transceiver, like we were listening to on the web SDR, notice that I changed filters. I set the filter from wide, which was for single sideband, which was 2400 hertz, and then I narrowed it down to about 300 hertz or 500 hertz, so I could listen to Morse code. Notice that I could no longer hear the voice signal, but I could hear Morse code just fine. And that allows you to basically tailor your receiver for listening to a particular mode. Now, we also experienced a little bit, and we went to WebSDR. And by the way, we're almost done with today. And I'm going to go to that same site, and I'm going to mistune. We went to the wrong sideband, but now I'm going to intentionally mistune something. Here we go. I'm going to intentionally mistune a signal.
I clicked on it and couldn't get it
Okay.
to LX right.
Here we go. What does it sound like? Or if I do this. Gavin? What does it sound
It
like?
sort of sounds like the robot from Star Wars.
Okay.
The tall one that keeps floating.
Yep, okay. And after that?
Sounded like high pitch.
Yeah. Okay, so each of those was basically off frequency. In order to adjust the frequency, there's something called, and I'm going to bring this back up, RIT, which is receiver incremental tuning, or a clarifier. That basically means that you guys that are talking are not on the exact same frequency, and somebody sounds too high or somebody sounds too low. And it allows you to alter one of those frequencies without changing the other one. It allows you to change the transmit frequency or the receive frequency without messing up the other one, which allows you to kind of like, you know, get somebody tuned in just right, but not move you off frequency so then you sound wrong. Okay, PTT, that is push to talk. That switches the transceiver from receive to transmit when grounded. So basically when you put a signal to 0 volts, that switches your radio to transmit. And I think that is going to be it for the day. Tomorrow we're into station equipment. And unless you guys want to do this today, but I know it's like a little afternoon. So tomorrow
I prefer tomorrow.
Tomorrow, okay. Tomorrow's going to be test equipment and stuff like that. So we've got about, what, 40 pages to cover tomorrow? Is that about right? Let's see.
Yep.
Yep. So tomorrow's gonna be a lot, all the rules and regs and stuff like that. Let's see. What page are we on now? Operating controls. We did that. All right, so we are up to page 81. So yeah, tomorrow's about 38 pages, and it's rules and regs and stuff like that. So, and go ahead.
What's in the I see on the ARRL web page, they've got a couple books, and that antenna book, there's a lot of pages there. Is that pretty?
It is. The ARRL antenna book is a really good book. I actually own a copy of it myself.
I have one from the 60s.
You know what? There are some new antennas, but by and large, antennas haven't really changed a whole lot. You know what has changed a lot?
Materials.
Well, you have this. Let me bring this up. And let me make sure this works. Okay, here we go. What has changed is the fact that we now have this. I'm going to close that. I don't need that open. Okay, can everybody see those screens on my screen?
Hmm.
And I don't need that open. And I don't need that open. Okay, so this right here, this is called 4NEC 2. This is actually free. This is software that you use to model antennas. This used to be the purview of Lawrence Livermore National Laboratories. This ran on a big mainframe computer, and you would basically use the Fortran-based software to model up an antenna, and it would split it up into little segments, and it would take those segments, and it would give you a simulation of what your antenna would look like and how it would work. Let's see if this works. Yeah. Are you going to argue with me? Oh, maybe. Nope, not going to work. Darn it. That means I didn't do a very good job of modeling it. But anyway, what's cool about this software is that, let me see. Here we go. What's cool about this software, notice this is a quarter wave vertical antenna. This allows you to do stuff like, okay, show me what the radiation pattern looks like. Okay, show me what it looks like in 3 dimensions. And somewhere I've got this, which is view, window, 3D viewer. Let's see if it'll run. And we want to show segments. And let's run it again. See if it'll work. And I don't know if this is going to, oh, here we go. Hide pattern, show pattern. So here is my antenna pattern. It'll actually show me what my antenna pattern looks like for the antenna that I just built using the software. So what's cool about this is that I don't have to go through the process of necessarily trying something and guessing what it's going to look like. I can use the same tools that were developed in the early 70s that were way too complicated to run at home because the hardware didn't exist, and actually do it. And just have my computer do it and do modeling for me.
Can you put in the parameters and then it'll build it for you?
Depends. One of the things that you can do with this is that you can run this optimizer and you can decide, okay, well, what's important to me? Well, I notice I've got this angle. I said I want 50 ohms. So half of what's important to me is this reactance and half of it is SWR. So I could say I want 100% there and 0% there, and I want to go. No variable selected, so I want to pick the radial length. No, I want to pick the angle. Here we go. So I want to optimize those 2 values, and it actually goes through and does iterations and figures out the best possible result. So basically what it's doing is it's altering my radial length and the angle and saying, here's the best antenna that you can come up with. And I don't know how long it's going to run. I guess we'll find out. But this is, again, this is free. You know, there's so many cool tools out there for doing stuff like this. And I guess we can stop it. It's not going to get any better. And we'll save it. And now we'll exit. And then we can run it again, and we can show what the pattern looks like. There's other cool stuff out there that, again, were, you know, not in public domain, but were generated by the same kind of operation. So let's go. I'm going to go to another website. Sorry, enrichment activity, right? Okay, VOA Cap Online. Everybody remember the Voice of America?
Sure do.
If you're old enough, you remember the Voice of America?
Yeah.
Broadcasting all the propaganda of the United States to the world, just like Radio Moscow did. Except that I think ours was a little more truthful than Radio Moscow. But anyway, there's a lot of money spent on sending information from the United States to foreign countries to try to convince them, hey, you know, the United States is not a bad place, and, you know, this is what it's really like here. Well, a big part of that is figuring out, let's say that you want to send a signal into, let's say at the time we'll go with Bulgaria. And where do you want to put a transmitting station in Canada, or let's put it in Maine, so that your signal gets into Bulgaria. And you want to transmit with, let's say, 1,000 watts, and we're going to be using AM. And we want to know between those two places what our signal is going to look like at what time of day. When are people going to be able to hear us? So we look at this, and this allows us to pick our frequencies. Now it's optimized for the ham bands, but these are basically very close to shortwave bands as well. And they could say, okay, well, at 1800 UTC, which is about 1 in the afternoon, that is a pretty good shot on the 17-meter band, which is about 18 megahertz for this particular setup. So 1,000 watts on AM. So, okay, but if we wanted to go to a lower frequency, let's say 60 meters, that's 5 megahertz, there's not a lot of good choices. So maybe for that particular situation, we need to put something in, let's say, Scotland. Oh, yeah, look at that. That's much better. Or maybe we can actually get something over in Finland, put an antenna over there. Oh, yeah, that'd work really well. So that's how the Voice of America would decide where to put their transmitting stations. Now, what's happened over the years is that since the Voice of America really doesn't do this a whole lot because of the internet, we can do other cool stuff because they've essentially turned it into a propagation tool for everybody to use. So let's say, okay, I want to try to make contact between the United States and Madagascar. Here's the propagation wheel. We're going to select our particular transmitting power and mode of operation. And this gives you the optimal times and bands to try to make contact. And maybe the short way around is not necessarily the best. So this thing that says SP, that's short path. LP is long path. That's basically going the longer way around. And you might actually have a better shot at certain times and certain bands because you're going over salt water as opposed to going over mostly land. So these tools are out there and make life a lot more fun and a lot easier. And also they can take some of the guesswork out of doing things, but can also, you know, give you some other ideas that maybe you haven't thought of before.
That's pretty awesome.
Isn't that cool? And then there's, you know, all kinds of propagation, additional propagation tools, you know, real world propagation stuff out there. So the other one, of course, is this, which I briefly showed the other day. And this is a real world propagation tool. So we're going to take a look at signals received in grid square J065, which I believe is in Germany. So this, and these are all sorted by different bands and modes. Different colors are different frequencies. So you can see that the lines that go off one way are not necessarily the same color as the lines that go the other way. You can see where the day-night terminator is. You can look at, let's say, we'll look at PM95. This should be around Tokyo, and can see what people in the Tokyo area have been reporting. So a lot more of the blue ones. The blue ones are 40 meters. So from Japan to Europe on 40 meters, a little bit of Japan to South Africa. And notice that we haven't really lit it up yet. There's a couple of people who are receiving between us and between the West Coast and Japan. And you can also see that if you hover over it, it'll say that we're on 14.075 megahertz. That gives you the frequency. It gives you the signal strength. So this minus 19 dB, that's pretty weak. Let's look at another one. Minus 15, that's also pretty weak. Whereas, let's see this one. Ooh, plus 6. That's a pretty strong signal. So for whatever reason, the person who's been reported there either has a bigger antenna or a clearer path. And these are all real-time propagation reports.
Well, I was watching this podcast, and this guy, he was working with Naval Special Warfare, and he had started working with some contracts with the Pentagon, and he developed some software that anytime anybody, like the SEAL team was broadcasting on whatever bandwidth, and anybody that was recording their signals, they could triangulate on who was recording it. And he said it was simply math, and I just failed to understand that. Do you?
They could record they could actually triangulate who was recording it?
Yeah.
I don't know how you would do that.
Yeah. I'll send you the link.
Now, I will say that, if you start looking at, I would actually be really curious to see that. I will say that the FCC is really good at triangulating stuff because they have some very, very good tools that, if there's a signal that is emanating from somewhere in this area on any band, the FCC is really good at basically using its listening stations and pointing antennas and figuring out where it's coming from down to within a few mile, like a 10-mile radius over a distance of hundreds of miles. And then, of course, you can take the mobile units and zoom in over there and over here and over here and do something called triangulation from that point, at which point you're basically much closer, and then you can zoom in even closer. This is actually what we use on the ham bands to do something called fox hunting, which is go find the hidden transmitter. And we make a sport out of this. It's radio direction finding. And every year, as soon as the weather gets a little bit better, we go out and we have somebody hide a transmitter somewhere, and we drive around or walk around a park or whichever way, if it's a big operation or a small one, and we go and take readings, and we go figure out where the hidden transmitter is. It's actually a lot of fun. The practical application is for, let's say somebody's transmitter is malfunctioning. It gives you skill in going and finding it. It also, for people who do search and rescue, allows them to go and find the person who's buried in the snow. Search and rescue. Any other questions or thoughts or anything like that? Is everybody still having fun? I hope.
Yep.